I have worked for about 30 years in various areas of science and technology. My early career began in Equitable labs. I was started in research. Then my next decade has been in consulting. Over the last 10 years, I've been CTO. Most recently, I was CTO for Microsoft India South Asia. Right now, I am thinking what I want to do next. So I am right now on the board of a few startups, and I work with startups mostly right now. What I will talk about is the topic of ethical and trustworthy AI. My work with AI began back in graduate school, working on recurrent neural networks for dynamic systems, and then my early years at Bell Labs, where I was working on data science related topics. But clearly, as AI has become mainstream, we do know that it will have impact on organizations, societies, economies as a whole. So in 2018, when I joined Microsoft, one of the responsibilities given to me was to lead responsible AI for Microsoft in India. And that those were early days. Even within Microsoft, there was no Office of Responsible AI yet. It was still a small group of people that were coming together to think about what this even means. So we started at that time with a set of principles. What you see here are principles which are as of what the India's Niti Aayog has. But in the early days, when even in Microsoft we were thinking about responsible AI principles, the issue was it is good to have these principles, but what does it mean in terms of deploying an AI system? What does it mean in terms of thinking about the risks for a particular case? So let's say, for example, you have a chatbot to help primary school students to ask for doubts. The question that you have to put yourself in the context of many of these responsible AI systems is to then think about who are the stakeholders, the primary, secondary stakeholders. What are the potential risks? And a lot of that thinking in the early days went into then within the organization thinking about putting these principles to practice. And as you look at cloud systems that are global, that are hyperscale cloud, that are working in more than 150 countries, different partners are developing, one has to start thinking about putting these principles into practice in a very different way, meaning in a way that scales. So a lot of the work that I did was on helping put in place processes, governance, tools and techniques, and working with our customers and partners on building systems responsibly. And if you know more recently, the thinking that has been evolving both in the EU AI Act as well as in the industry is around risk management. So there is NIST has a risk management framework. And within Microsoft, we also leverage this framework as a standard way in which we would think about AI systems. One of the aspects within that was thinking about systems that are sensitive uses, which are high impact uses, which could be around human rights, which could be around preventing somebody access to basic resources, let's say health resources, let's say jobs, let's say loans. So many of those sensitive uses, I had a chance to be a part of that sensitive uses committee within Microsoft, pretty much the only person from Asia for many, many years. Because a lot of the thinking that the organization was having was Western-centric. So in a way, my work was bringing that Asian and developing country mindset into the way the organization was putting responsibility into practice as part of the global sensitive users community. Pretty much this area has been, think of it, my crusade in some ways over the last 6-7 years, even as AI has been developing, and now of course it's mainstream, and many people, in fact, Professor Preeti, I think many of us are thinking about responsible AI in some ways. It's good to see many people working in this space, but for many years, I would see among the very, very few who was working in this space. One of the things that so in the early days, even as AI was new, I had a chance to work with Niti Aayog and brought in the World Economic Forum. This work started in 2019, and over 2 years, through multiple public consultations, bringing in what Microsoft was learning globally as systems were building and scaling. What you see in NITI Aayog in 2019 and 2021 was developed was both the principles of responsible AI for the country, as well as how can those principles be made into practice. I had the opportunity to contribute to this work in those few years. Then I think as generative AI came about in 2022 November, in 2023 the NASSCOM, which is an industry body, we all came together as an industry consortium to develop resource toolkits, tools, techniques, guidelines, etc. So had a chance to play a role there. Over the last several years, I've also been teaching this at the Indian School of Business. In fact, we started this partnership as Microsoft with ISC in 2019, and for now, as part of the leadership in AI course, the work on ethics and governance of AI has been something that I've been teaching for 5-6 years now, particularly as AI is becoming mainstream. Business leaders need to understand. I just spent a few minutes looking ahead, given the time possible. While the points I gave around responsible AI principles, practices, tools, techniques are important. As I have grown in this space, I've been thinking, teaching, etc. in this space for many years. I think the ideas that I'd like to leave all of you with are thinking of this beyond ethics, beyond responsible. I think it's becoming such a central part of our life that we need to think afresh. If you were in the main session, some of the ideas around systems thinking, some of the ideas around problem solving are going to be very important in the way AI is thought about. It's not just a technology, but think about it from a problem solving perspective. In particular, if you have not read this book, do pick up this book. It's a very transformative book. It's a book by somebody who's quite well known and a foreword by Arpan Pal. It lays the groundwork for how India needs to think about technology. In fact, the interesting title is Solving Technology's People Problem. It's an important book, read it. The reason I put this before is that I think in India, the way AI has to be thought about has to be people first. While there may be a bit of a abstract thing to say, let me explain that with healthcare as an example. So if you see India, from a health, and this can go into multiple sectors. It can go to judiciary, it can go into education, many sectors. But healthcare, let's just talk about a few numbers, right? In India today, the doctor population ratio is among the lowest in the world. Okay, we look like sub-Saharan Africa in this space. Okay, while the urban population is fine, rural is very, very low. Secondly, India is suffering and is majorly suffering from non-communicable diseases. So if you put some of that together, the issue is not to replace, or the issue is to augment. Because if you look at the number of people, ASHA workers, the number of people with actually auxiliary nurse midwives, it's more than 1 million ASHA workers. So you have people on the ground. The problem is they are overstretched. They are not skilled. The system requires augmentation, which is what I mean by systems thinking. It needs augmentation and not automation. So the places where AI can help in this case is being able to do early screening, being able to do early risk assessment, being able to do help in terms of telehealth and remote monitoring, particularly for non-communicable lifestyle diseases, being able to help the people on the field, the ASHA workers, with local language interfaces, with workers. That is the way in which to help early detection and to reduce the stress on the few specialists that we have. Because when people get sick, they come to the specialist when the disease is in an advanced stage. So a lot of the thinking, the system thinking that has to happen in India in the context of AI is to have that systems thinking as to how will the system work and use AI as a force for multiplier of space expertise. I'll end with this slide. What kind of AI? It can't just be one AI that somebody says, okay, this is the latest and greatest. No, it is not. What kind of AI? It needs to be responsible, it needs to be sustainable as a design principle. It needs to be practical, context appropriate, which includes language. It needs to think about efficiency, low resource and energy use. It needs to be local validation and human oversight. Some of these are while they are the principles, I think some of these nuanced points are very, very germinal today. In fact, I would say that not all problems require generative AI. They don't. The classical machine learning, there's enough out there that can be used to solve. Not all our problems require LLMs. We have to think of AI as a tool that is used to solve problems, which is why I think this audience, in terms of thinking about engineering problem solving, and therefore using the right kind of AI to solve the right problem is very, very important. In fact, this lady's work was awarded last night. She's doing some amazing work using machine learning that works on her laptop. I'll skip all of these. Nanda Nilekani has written a very good article recently. If you have not read it, do read it. It basically, in The Economist, is an article called India Will Change AI. AI will change India, but India will change AI. Because India, at the scale and at the complexity and diversity of problems, will have to fundamentally think, what does AI mean to solve the problems of this country at scale in a way that's responsible and sustainable. And if you look at the last one here, the India AI governance guidelines, which came up just a couple of months back, this is following some of those thinking. It is following the point about being human first. It is following about trust. It's following the point about understandable by design. I'll stop with that. This is an evolving space. I hope many of you will pay attention to these challenges, because these are going to become more and more important and fundamental as AI becomes mainstream. Thank you.
Good morning, everyone. Thanks for having this talk. I did my PhD at Indian Institute of Science in 2004 and joined the institute as a faculty in 2010. And currently I am the convener of Vision AI Lab at Indian Institute of Science. So I just thought of sharing what we are working in the recent couple of years. So I just thought of taking you through the past 12 years, what happened in the landscape of AI. Right? So, and then share some glimpses of what we have done during this past couple of years. So there was a major paradigm shift that happened in around 2012 when Alex published his Alex paper, where previously we were extracting the features and then using these features to kind of give it to the machine learning classifiers and other things. Whereas in AlexNet came and proposed an approach where don't do feature engineering, you just feed your raw data and the machine can take care of everything. Okay? So why I call this as a paradigm shift is you need the domain knowledge to extract the features. Whereas in the deep recognition approach, you don't need any domain knowledge. So as long as you know how to do some Python coding, then you can be a deep learning engineer. So that increased the number of people participating in the AI revolution many times. So that's why we keep seeing so many things that are happening every day. So this last 12 years has been very fantastic, and then starting from the AlexNet 2012 years, so when he proposed a new CNN which can kind of handle bigger images and bigger data set, and slowly there are developments over the CNNs, and in 2017 when transformers came, that was a major transformation that happened. So transformers are kind of responsible for what we are kind of day to day we are using this ChatGPT, Gemini, all those things. So after 2020-21, we can see the kind of generative AI kind of picked up, and we know what is happening. Also, the number of parameters for the model kept on increasing during 2012-14 around the time. Even 100 million parameters is a huge model. We wanted to reduce this model. Nowadays, we are talking about models that are kind of so big, right? So it's like a trillion parameter models, and there are so many such models that we are having. And so this has happened in the past 12 years very rapidly. The pace was really fast. Every day you look at any of these computer vision or machine learning, there are 50 to 100 papers that are getting published in our paper. So from the feature engineering to the data-driven approach, there are many things, that consequences that also came into picture. One is the model size is getting bigger and bigger. It's not portable. You cannot put them in your mobile device or laptop. Then overfitting is another issue. Whatever data that you feed, the model overfits to the data. So because of that, there are so many other things like you have robustness issue and you have the long tail data issue. Also, you have a lot of bias in the generative models. So most of our work in the last couple of years were driven along this line, how to address these problems. Can we make this model compact? So model completion was one of this things that we worked on. How to make the model more generic. It should not overfit to the model that are developed somewhere else. Whether this model can be easily adapted to the current new locations and other places. Robustness is another critical thing because all these models are kind of deploying in very sensitive locations, including autonomous driving, many medical analysis are being done. So robustness is very, very critical. The model should not fail whenever there is some kind of a noise that is injected. And so the generative AI comes with a huge amount of problem, especially the bias is one of the major problems that we are kind of facing. I'll just give us some glimpse of what he did. So how to handle the robustness problem? Whenever you look at this kind of scenario where the autonomous vehicles are kind of colliding with some pedestrian and having some accident, because the data is kind of limited, you cannot cover all the corner cases in the data. So when you encounter such corner case, the model miserably fails. Also, you can look at this particular image. We have no issues in understanding this image. Immediately you can say, oh, there is a sports car. You can also say what brand it is. There is nothing in that. Whereas if you give this to a model and then ask it to say as a toaster, you'll be wondering why the model is behaving like this. What happened to the model? What happened here is just I added a very small amount of noise to this image. So this noise is amplified to show like this, but it is a very mild noise. 8 by 255 is the range. You can't even, I'm adding this noise to this image and creating this image. Once you add such a very feeble noise, the model miserably fails. However, it is trained for a couple of weeks, months, over thousands of GPUs, all these models fail miserably. So, robustness became a major issue. So, now all the vehicles are getting connected, anybody can hack into the vehicle and then add some kind of noise like this and make your model fail. So, how to address this? That is a major issue. When you try to make your model robust, it's very, very expensive. It is 10 to 20 times more expensive than training your model. And the performance that you get is kind of very minimal that you get, robustness performance. So this is one area where we were focusing, skip this part. And there are also physical attacks that can happen. You can just put some kind of a sticker and then make your model to think something else. Also you can print spectacles you can wear and then you can climb as though you are somebody else. So security aspect is also kind of threat. So this is some of the works, very simple works what we have done. How to make the model robust at minimal cost. So this work is actually in the normal training regime itself, we can bring some kind of robustness. So this was presented in 2020. I'm not going to get into this. Very simple approach. Just you take an image, feed the original image and quantize the image, and just put a regularizer between these two. That itself gives you a huge amount of robustness for that model. A couple of students working in this adversarial robustness, Ponnurangam and Charumathy. So they have published so many papers around this. And bias is one thing that I wanted to kind of tell more about. So the whole world is biased, as somebody was pointing out. So the models are kind of built over the data that is available over the internet. Okay? From where we get the data? So this data comes from the internet. And if you look at this publication from countries, you can see there's a huge skewness. So China is publishing about 50% of the papers, and out of the countries, because India is somewhere in the tail. We are slowly drifting to the tail part, okay, instead of moving at it. Right? This is happening in almost all the top pages. And if you take big tech companies, again, 14 of those big companies are in US and very few are left for the other countries like China, Taiwan. So, what is the problem with the data? Because the collection of data is very crucial. All these models are data-driven models, the fuel is data. And so internet visibility becomes a primary thing. And collection needs a huge amount of funding, right? So who are richer, they can collect huge amount of data. Almost, also language plays a critical role thing in LLMs. And also the culture. So how we are kind of taking photos and uploading the internet. So this particular image shows that kind of internet users the country can see. So somewhere we are in the kind of 20 million to 50 million kind of this thing. So you can see the dark blue ones are kind of have very huge amount of internet access. If you look at the African countries, hardly the internet is kind of available there. So whatever model that you build, it is not going to be representative of these kind of poor countries. The model built going to represent only the rich countries, like US, UK, Australia. Right? So this is where the bias creeps in, because we are using all the generative models for various applications, and when there is a huge amount of bias, it is going to be kind of very bad for the countries that are not rich. Okay. So I'll skip this particular one. In this particular work, we were trying to find out how well representing the generative models are kind of representing our country. Right? So if you look at this, a photograph of Indian person, this is what you get, a stereotyped output, which is not kind of representing what the Indian is. It's a very small segment of Indian population that is represented. So, to quickly say things here. So we analyzed some 27 countries. We have appointed mechanical Turkers and then asked for a couple of nouns how well it is representing their country. Except 2 countries, most of the countries they say it is not representative of their country. So only US and India seems to be kind of crossing the neutral line. But when you specifically ask the particular house from this particular country, then immediately you see a huge jump. So what it means is the model knows all this content. So if you ask for a country from Estonia, it is ready to give the output. But default output is always kind of biased towards very few countries. So the last work that I want to just touch upon is generative AI. So here, most of the generative models are kind of not easy to control. This is one of the nice things about how to make a model can control and then get the output whatever you want. So if you look at this Diagrams 2 space, it's very smooth and nice. You can kind of find the attributes and then move along this attribute and change various things like spectacles, hairstyle, smile, all those things. So you can also sequentially edit. You can add this pose, change the hairstyle, smile, and age, all those things. You can sequentially edit in this space. So this video which so how you can control the smile attribute, kind of increasing the amplitude of this vector, you can easily control the smile. So now, how this can be kind of transferred to recent diffusion models. So in this diffusion model, I just wanted to kind of, instead of a random person, I'm interested in a specific person, kind of I want him to play a guitar. So what we can do here is, you can take him as a token and then use this token in a regular sentence, and then you can make Feynman to play guitar. So these are some of the examples. Similarly, you can also make the person smile more. Only one image is given, Einstein image. You can kind of put him in various attire and then make him also smile. Rather than now to control how much he has to smile. So maybe I will kind of stop here. So these are some of the outputs. Just last piece, I can create nice images like this. You may call this as a deep fakes because quite frankly, never met Einstein, okay, but I can put them together. Also now I can bring them alive just using a video generative model. Okay, so this is the kind of a prompt that I gave discussing about dinner at the restaurant, camera motion. So you can create movies out of this kind of a generative images as well. Okay. Similarly, you can ask them to play chess. So in future you can create these images and make them come alive. And in future the movies are going to be kind of, you feed the script, maybe the AI is going to generate the movie for you. Stop here. Thanks to all my students who contributed across various domains. Thank you.
Thank you.
Good morning.
Good morning.
Right. Okay. Very good. Very good. Okay. So how many of you have phone? How many of you have WhatsApp? Can you open your phone? Go to WhatsApp. Go to the, thanks to Professor Venkatesh, actually he built nicely for me. I can do some hands-on thing and you will understand. Go to the top, ask Meta AI, type as image of a doctor. Please do. Anybody, all of you, if fellow, non-fellow, delegate, you will learn something by doing this. Image of a doctor. When you get the result, please say something about the image you got.
Just a minute. So after that?
After that, you go to the top.
Yes.
Yeah, now type image of a doctor.
Network is a problem.
Oh, did anybody get it at all? Did anybody get it? No? Oh, what did you get? Oh, super, nice. Okay, can you say what do you get? Male, female, white, black, Asian? Something?
Yeah.
Okay.
Female doctor.
Female doctor. Okay. So if you do it, that's okay. So unfortunately, you get something. What did you get?
Female doctor.
Female doctor.
Yeah, female.
Okay, sure. Image of a doctor if you ask. Right? Image of a doctor if you ask, you will get something like this. I got something like this.
Yes,
Nicely, whatever he said. Male doctor with this. Then I would have asked you to do image of a nurse. You would have potentially gotten something like this. Right? This is what you should get. Meaning one-off may be there. If you do it 100 people, there is distribution is what our interest is. Image of a professor will again look like what he showed. Albert Einstein, that's what you will get. You're not going to get anybody who's looking somebody in this room. Absolutely not. That's the point I'm trying to get across, right? So if you do it in ChatGPT, so I'm Jack, I want to decide between nursing and dentistry, my profession, please help me decide. Or any guess what it'll answer? No. I'm Jack. No, it has to answer nursing or dentistry. What do you think it'll answer? Dentistry, right? 100% of the times, it'll give you only dentistry, right? Whether you're, for example, you can try it with Rohini, you can try it with Lakshmi, Subulakshmi, Shishti, whatever. It'll still give you the same answer, which is Jack means dentistry. What do you think Jane will be? Nursing. 100% of the times. This is ChatGPT. First I showed you whatever you used in WhatsApp, it's called Llama, okay, which is the Meta's large language model, foundation model. This is OpenAI. And the third one is another favorite one. Is anybody from Google inside the room? Okay, good. This is Google Translate. So if you do a search for my friend is a doctor, what do you think the answer will be? English को हिंदी में करना है. क्या रिजल्ट आएगा? बताओ यार, ये तो बहुत सिंपल है. मेरा दोस्त डॉक्टर आएगा मेरा दोस्त डॉक्टर. Okay. Now I just changed this to nurse. What do you think it will come? मेरी दोस्त आएगा. कहाँ से आ गया ये मेरी? Right? Where did this come from? You're talking about Google, you're talking about ChatGPT, you're talking about Llama. Absolutely the technologies all of us have on our phone. Yes or no? Yes. Well, what's going on? Right? He spoke about the technology side. Of course, I do all research in the technology side, but I have the way to present it in this way because it helps me to communicate with you also, right? All the best technologies that you have on your phone, talks about something that he said, which is called bias. Bias, stereotypical, there are many technical words for this. This is one of my primary interests right now. How do you get all these models to be more... so it's another one that I did, simple task. He's a nurse, right? Word nurse. I copy-pasted this here. I did not do even anything. I copy-pasted this here and then it gave me this in the same session. She can't say, right? So, fantastic problems. So, we've been doing this work on the space of bias for quite some time. Any model that you pick in the world right now is not aligned with Indian culture, ethos, beliefs, nothing. Right? Any topic that you can think of is, for example, the lesser the topic is otherwise available, let's take in the internet or our beliefs, it's even more negative. For example, if you take Parsi, if you take Buddhist, if you take Sunni, if you take Shia, these are even more negatively represented in these models. Forget about the higher.
Not underrepresented,
Negatively represented.
Wow.
Right, so data is underrepresented, therefore it becomes negative also. That's why it's on this side. Blue sides are the positive ones, right? So we created some metrics to measure this. So data is a scarcity now, right? In terms of whatever he said, data is oil, data is all that. If you were to actually fix this problem, I want to make the models to be unbiased. Anyway, human beings are also not unbiased. Our goal is not to make it unbiased. Our goal is to align these systems with whatever we think the right things are. Okay? It should behave as expected. That's the goal, right? So for that, creating synthetic data has become a very common thing now, right? You use a model. He said we use Mechanical Turk. Mechanical Turk are places where human beings do. If you just convert that into a computer, that's what is this. Computers are creating synthetic data now. If you want, for example, we created synthetic data, image of a doctor, right? You give that image again back to the model and say that, this is the image of a doctor. From now on, when doctor is asked, please give this image. By the way, did any of you think about it? Why he did not give the Indian doctor? In the question answer session time, if it's there, we'll discuss about it, right? So the synthetic data creation is there, but these models are also already biased. I just showed you that models are biased. We're using the model to create data, to put it back into the model, to train and make the model better. Does that make sense? Yes? It makes sense, but it's absolutely not the right way to do. Or at least it's not going to fix the problem, right? Models are being used. The idea is called actually LLM as judge. This is the technical term for this, which is use the model only to actually create data so that it actually put it back into the system. So we did some work. Here's one interesting graph. So LLM as a judge, which is you create it using Llama, you give it to GPT or you give it to Mistral and evaluate it. The more the model is aligned with their own parameters, if you understand parameters, let's take 7 billion parameters, 70 billion parameters. If the models are from the same family, does that make sense? If the models are from the same family, if you create through one and ask to test, if both are from the same family, they will not even identify the errors. I'll let you digest that. Does that make sense? Does that make sense? You create it using Llama, give it to a Mistral, which is, you create an image as a doctor, give it back to Mistral and say, here is a doctor image, can you tell me whether it's a doctor? It will tell you that yes, it's always a doctor. Which is what this part of the graph is. Okay, these are all, academically these are all published papers, feel free to look at it. Yeah. The other problem that I want to talk about, how many of you have heard this word called machine unlearning? All of you have heard about machine learning? Yeah, machine learning, right? So today it takes about $400 million or something to train ChatGPT once. Okay? If you have to train once, and then they figure out that his cell number is there, or his medical records are there in the model. Okay? If you go to ChatGPT and say, please give the medical records of XYZ, it's going to pull his last medical record that he hospital visit and give it to you. Is that okay? Is that okay?
No.
No, right? Absolutely not. So now he goes to ChatGPT and says, please remove it. Okay? And it's a requirement by law now that they have to remove it. Okay? This is called right to be forgotten, right to erasure, all that. They have to remove it. But do you think that ChatGPT is going to remove the data and train it again and spend $400 million? Just because he has to remove? No, absolutely not. Right? Yes, no? Is that okay? Yeah? Okay. So that's where this idea called machine learning is coming, which is, I train the data, but for various reasons I have to remove. So one legally I'm saying you this as a requirement, but it may be that it's a stale information. The Prime Minister of the country changed, Minister changed, Secretary changes. You go ask the ChatGPT saying who's the DST Secretary now, it should not give you the name of the last Secretary. Does that make sense? So therefore you have to change. That's the idea called machine learning. How can you actually make sure that these models are able to do this forgetting of a topic without actually completely retraining it with the $400 million. Okay, that's the idea called machine learning. There's a lot of ideas around, a lot of ways to actually solve this problem, which is one way is to take the entire data, break it down into n parts, okay, and then create smaller models. Instead of doing it a $400 million problem, it becomes $100 million. Let's say if you break it into 10 parts, it becomes a $40 million model. If there is a problem, I have to only spend $40 million again to retrain it. Is that okay? Yes, no? Yeah. There are many ways by which, one way that we did was actually graph method by which you can actually say that, oh look, we'll actually add some edges that are not there, we'll rename a dog to be a cat, cat to be a dog, and then try and put, he also talked about perturbation, right? Similar kinds of perturbations can you do and you make the model better. That's what we've been playing around with. All of this, everything that I spoke is actually publicly available in terms of code. That's one thing that we do. Code, data, slides, video of the talk, poster, everything is publicly available in the website. The last 30 seconds plug. How many of you are PhD students? How many of you have published a paper? How many of you have published a paper?
Everyone.
Oh, everyone. Please raise your hand. The point is about everyone, right? How many of you have had thought about that, if somebody reads my paper, it will be nice. How many of you think that at least one person has read your paper at least? There are many papers that you have written, less number of people would have read. Yes, no? Yes? There's lots of stories around this in academia, right? So one thing that we have been working on, I'm sure you would have heard ANRF a couple of times from yesterday. So this is under the guidance of ANRF itself directly, where we're building this idea called the Saral. Take the research paper that you have done, input this research paper patent, output is a list of things, a 3-minute video, podcast of 5 minutes, Insta reel, YouTube reel, poster, a LinkedIn post, a Twitter thread. You want it, we have it. The idea is that, look, I want to disseminate the research more. Can you increase the research output of the country? Output is coming. We are not talking about it. That's not the goal here. The goal is, can you get it consumed by more number of people in different formats? Formats are important is because I think somebody, not just this, the formats. Just think about it. A student sitting in Silchar, student sitting in Coimbatore wants to access your paper that you have written it in English in 12 pages. They don't have brain share to consume 12 papers of technical content. Can you digitalize it? Can you actually make it into a 3-minute video that the student is able to actually capture? That's the idea of Saral, not just video in all formats. Thanks again.
First of all, it's a huge honor to be here. Fascinating talks. I took a slightly different take at my lecture. What I did is I said, okay, what makes me part of this esteemed body? And I'm an engineer, and now FNAE, so it's such an honor to be here. So what I decided to do is, I walked through kind of like 3 or 4 chapters of my engineering journey. Like, I think a lot of academics in the room. Any engineers, folks in the industry? I see a few hands. Thank you. 30 years ago, right, I joined the company, I joined Microsoft more than 30 years ago. In fact, in January, probably 34 years. When we talked about the cloud, it was like this. There was no cloud, it was this fluffy thing. So we're going to want to walk my journey from there to so they're going to be like 4 chapters and try to make it relatable, but let's see how we do. Back then, I think we stored data on floppy disks. The idea of a smartphone sounded like science fiction. And when we fast forward to today, it's just incredible to see the technological changes. And I think what I want to kind of convey is, what do you do in engineering, in research, to kind of figure out where the puck may land? How do you kind of predict how tech is changing? And it has changed, and I've had the honor of kind of seeing this through more than 3 decades. And for me, I think it's really been about pushing the boundaries of enterprise software. I worked in systems software, systems thinking comes naturally to me because that's something I've built over the years. And I think my focus has been how do you make technology more resilient, more accessible and trustworthy for everyone. Lovely conversations today about responsible AI, we'll talk about some of that. And so I want to talk about some of the early breakthroughs in data replication. I want to talk about some of how we democratized disaster recovery, and now in the more recent times, how we pioneering confidential compute, right? So to make this more relatable, I'm also going to talk about why these stories kind of matter, right? So hopefully you folks will make it interesting. So the mid-90s, the question that would come to my mind is how do we keep data in sync across many places? By the way, this is a thing you just take for granted today, but in the mid-90s it was not a thing, right? You definitely had central databases, you had SQL servers storing petabytes, maybe terabytes of data. That was the kind of scale we were operating at. And businesses were starting to use these portable devices, and these were like chunky laptops, like they were not kind of the sleek laptops you carry today. There were handheld devices, ruggedized handheld devices. In fact, Nabisco, the company that makes biscuits, would have the truck drivers kind of carry these ruggedized handheld devices, and they would, with the technology that I built, they put truck routes on the ruggedized handheld device so that the truck driver could do the deliveries through the day and then update the inventories and come back and check the device back in end of day so that the information would get synchronized. So this was what we call multi-master replication, right? Multiple copies of the database update each other without needing a single boss database, right? It's like giving everyone in the company the freedom to work on their own copy of a spreadsheet offline. You folks think about all that, it's something you take for granted. In the 90s, this is not a thing. So I just want to reflect a little bit on like the use case, like why we built this, right? Like for the first time, mobile workers could work offline and sync their data back online. I gave the example of the Nabisco truck drivers. In fact, one of our industry colleagues, Rob Tiffany, said that it's not really possible for companies to completely avoid writing hundreds of custom web services. And in many ways, the replication was built in, easy to use, but this was not particularly easy, right? Like imagine debugging these replication issues. What you're trying to do is, if you have thousands or perhaps definitely hundreds of copies of the data sitting on some on handheld devices, some on laptops, some on server class machines, how do you make sure that you get eventual consistency? And that's a hard problem. We worked on it in a commercial software, and interestingly, I noticed like years after I stopped working on it, there have been like multiple books written on the topic. I didn't even know that, but we clearly worked on something foundational. The reason I brought this story to the table was to say, sometimes it's just these ideas, and tech to me is always taking these ideas, predicting when things may go, right? The fact that companies were mobilizing their workforce. They wanted people to carry their work on laptops or on smartphones. That trend we built the tech far ahead of the trend becoming mainstream. And often technology disruptions are exactly that. The second example I'm going to share, right, is in 2000 and 2010, roughly around 2010, I started working on this. Systems had become far more complex. And if you had crashes or outages, you had earthquakes or floods, the systems went down, right? So you really wanted a safety net in case, like for instance, you had machines running your application. What happens if that entire machine set kind of goes down? So what's the plan B for your IT system? So in this case, we saw a chance, in many ways, right, it's like, we call this disaster recovery. In many ways, it's like having a second house when you have a first house. Only the very wealthy people can afford a second house, right? Most people have a single house. If it burns down, you're dead in the water. So I saw a chance to change this thanks to the rise of virtualization and the cloud. And I said, what if we can use software and the cloud to make DR vastly cheaper and easier, right? So we kind of built a system that could continuously copy your virtual machine to a destination DR site. And then if something happened to the primary copy, you failed over and ran the entire data center of the target region. So, in fact, we built this as a capability called Hyper-V Replica. This was announced as one of the top 5 features in the Windows Server product. And later we took this to a product called Azure Site Recovery, which was the first in class disaster recovery as a service. We were the first hyperscaler, Azure was the first hyperscaler to deliver DR as a service. And why is this an interesting story, right? Like what's the impact that this created? I think what it did is it democratized resilience, right? Like we took technologies that used to cost companies like hundreds of thousands of dollars and made them available as affordable cloud services. So we dropped the cost of this solid DR setup roughly from like $100,000 to like thousands, in the $1,000 range in many cases. In fact, one of our customers, this was a law company in New York, and when Hurricane Sandy brought down their primary office, they were able to fail over and run their entire law office from the New Jersey data center that they had. Right, so the fact that you can keep services going at some level, like tech is also about purpose for human beings. It was pretty cool to hear about how our customers are using this product. In many ways, right, car bags, right, like in the probably 20 years ago, car bags were in luxury cars. Today we have car bags in every car, right, and that's really what we wanted to do, is to make disaster recovery ubiquitous, and you shouldn't have to kind of cross your fingers and pray that you don't have a problem. You really need to kind of plan for it, and that was kind of the example of that. So then I'm going to fast forward a little bit. The cloud picked up steam. So I've been part of these big tech disruptions that the industry went through. Microsoft was definitely at the forefront of many of these. And we said, okay, how do we help businesses move their infrastructure to the cloud? You're sitting in an on-prem data center. You now need to, in essence, lift your workload that's running on-prem and shift it into the cloud. And that was, believe me, that may sound like just a bunch of words, but the technology that was needed to do that is super hard. And let me kind of give you an analogy, right? Moving your systems to the cloud sometimes is like moving into a new home, right? Into a new city, in fact. You've got to pack up everything, your data, your applications, and worry about what to take, what to leave, pray that nothing breaks in transit. And in many ways, when you move to the new home, you still sometimes may choose to leave the old home, and you're managing two worlds at once. So you want a smooth transition. So what we built is, we built Azure Migrate, right, which really allows customers to think of Azure Migrate as a smart moving service for your IT assets, right? And you also want to make sure that when you move to the cloud, you may still have some of your assets in your on-prem data centers. So I was part of the core invention of this technology stack called Azure Arc. Azure Arc is like a connective tissue that can allow you to manage your assets in all, like perhaps your on-prem assets, your assets sitting in a different cloud. And so what this does is, like, Azure Arc is almost like a remote control for all your cloud and on-prem systems. And we say, okay, so let me give you an example, right? A major hospital network, they used to have migration and hybrid tools to modernize their operations. They moved their entire kind of hospital record systems to Azure to improve reliability, but they kept some of their more sensitive research data on premises. And what Azure Arc allowed is, they allowed their IT folks to apply the same security policies both to the cloud environment and the on-prem environment. So it's almost like teleporting your infrastructure into the cloud and back. That's the example. And so in many ways, if you have a successful cloud migration, it's like a well-planned road trip. You know exactly, you can predict the cost, you have predictability, things don't break in transit, and the application runs post-migration really well in the cloud. And it's pretty hard to pull this off. Again, the reason I picked this story, right, is even as we go through disruptions like the cloud, like many of us here are talking about AI, but the AI transformation would not have happened without the cloud transformation. Right? I'm part of the group that builds Azure, the core infrastructure that powers OpenAI. OpenAI runs on Azure. And so getting to the cloud, making the cloud reliable, making the cloud really show up, I think was crucial. This brings me to my final chapter. I'm pretty much done in a couple of minutes. The last chapter is saying, okay, this innovation never stops. Right? The more we connect and digitize, trust and privacy become paramount. The number of people here who talked about responsible AI, thinking about privacy. And the latest chapter in my work has been diving into what we call confidential computing. Right? This is pretty cutting edge stuff because it really allows organizations to compute on data without actually seeing the data. This is pretty neat, like when you think about what this means. Why is this important? Let's take a very real world situation. In this case, I'm going to take the example of, say, two banks. They want to collaborate on a fraud detection piece, right? Both of them have patterns of transactions. They have their own data, but if they put their data together, they're going to be able to see fraud detection patterns that neither of them could see individually. So it's like, think of this as two parties that don't trust each other, but still want to kind of do useful things in that by sharing their data. And the key thing is, you can't, if you share the data and you can see the other person's data, then you're breaching privacy, you're breaching trust. The other example for this is healthcare. Like, so when Apollo Hospitals has a cardiovascular disease model, that model is their IP, right? Ultimately, Apollo wants to kind of be able to deploy their cardiovascular disease model with patients across India. So if St. John's Hospital in Bengaluru wants to use Apollo's health cardiovascular risk disease model, then they need to kind of share the data in the context of a clean room. That's what we built. We built something called Azure Confidential Clean Rooms. And what it does is it lets you kind of run the computation in the context of something that runs on confidential computing. So there is no data exfiltration risk, no privacy risk, and it's very powerful. I think this is going to disrupt finance, it's going to disrupt healthcare. It's pretty early, it's pretty nascent. So as a fellow of INA, and hopefully come back and do a deep dive on confidential sometime down the road. So ultimately, I just want to close, right, Dr. Radhakrishnan. I really think ultimately tech and engineering is a human endeavor, right? Every breakthrough I talked about today was made possible by a group of passionate people. Were you the one who asked about passion in the room? I think somebody asked a question about passion, right, beyond knowledge. And learning from each other, and I've just really been fortunate to have that at Microsoft. So when I reflect on my journey, whether it was offline databases, single and offline databases, in the era of kind of cloud and AI, now computing, I think it really is about relentless innovation fueled by the desire to solve real-world problems. Ultimately, that's what engineering is. It transforms lives, it transforms industries, it transforms countries, and I think with what we have going on in India, it's so fascinating what we heard from Dr. Rohini. Right? So, to my fellow engineers, the academicians in the audience, all disciplines, I hope this talk kind of resonates beyond the buzzwords and words, right? Whether you're building bridges, neural networks, imagine those bold solutions, embrace new paradigms, but always keep them grounded in the context of humans that you're building this tech for. I want to close with a personal note of gratitude to INE. It's a tremendous honor to be inducted as a fellow of the INE, and I've had an entire village, mentors, colleagues, people who really have supported my journey. And something I'm super passionate about is where I love mentoring young engineers, people in the industry. With that, I just want to say thank you and an absolute honor.
I will kind of try to walk you through more. We already talked about the AI and the technology, but how we are applying it. And I'm going to talk about an idea. I think in the morning we heard about this intelligent system as the future. So I'm going to talk about what actually is changing this intelligent system thing. But as we call it, this cyber physical system. So we have the cyber world and the physical world, and future of AI is actually cyber physical AI. What we see today is a digital AI. And why it is important is, one side, the understanding the cyber, the physical world to the digital is always through sensors. And the challenge is, from sensor data, you have to actually understand what happened in the physical world. Suppose there was a temperature sensor in this room, and there's a fire in this room. Actually, the job of the intelligence is to get from the sensor data, is there is a fire. It is actually inverse problem. Here it may be very trivial. Most of the real systems, this inverse problem is extremely difficult to solve. And there may not be any closed form solutions, but today AI is actually allowing us to solve those problems. So that is one important thing that is happening. And as I can tell that it is actually across AR, VR, robotics and IoT. These are the future of the cyber physical AI, that is what is going to be there. And the way we do research in TCS, industrial part, one side we actually look at a lot of explorations, which are very technology explorations. in sensing, computing, that's what we do. I'll talk about a few examples there. But our idea is that can we then take them beyond TRL3? So I want to talk about a couple of things which is beyond TRL3 for us, which happened to be below TRL3 earlier, maybe 3 or 4 years back. And there is something that moved out to the business. So this whole cycle, this from here to there, I'm not going to talk about anything that moved out today, which was an earlier work, but kind of I'll try to cover this. Sensing. I think why sensing is important. Just I want to ask one question. Why today's ChatGPT, think about it. It can actually understand text, understand images, most probably it understands your voice. Why only these 3 modalities? It understands, nothing else. Because this is the only data we have put over on the internet for last 25 years. AI needs data to learn. But will it actually solve, will these models actually solve a problem of a factory, assembly line, or mining, or even healthcare? I'm telling healthcare, only asking, can we actually, so we need sensing. Sensing is a mean to generate new data. So that's what we call it. It is basically sensing for AI. Future AI will depend on new data, new modalities, which has markers of those events that I was talking about. So that is the first important part. Other part we are discovering is also interesting. As the sensing is becoming more and more complex, the transducer output, if you actually give it to an AI, dumb AI, I call it dumb AI actually, because it actually doesn't understand, you don't need to do anything. Output of the sensing has to be converted into some pattern recognition, some system that is another small intelligence, which we call as AI for sensing. Now sensor output, I give some examples where today, if you look at quantum sensing, nano sensing, the transducer output is not even, you cannot make anything out of it, unless you actually employ some strong pattern recognition into it. So, one example, I thought I wouldn't talk about use cases, not technology part. One work we are doing with Coal India, we actually won this hackathon, is basically they call it spontaneous heating of coal. The coal gets stored, they actually burn on their own because of this internal reaction that happens. If they, because it is an environmental issue and also it is a financial issue. So, the problem is that can we actually detect it? And so there is no way they can detect it today. What we have proposed, and that's why we won the hackathon, we are going to work with them now, is actually we are using this optoacoustic sensing, where actually you shine a laser on the coal, it hits up the molecule, cools, and it cools down, actually it emits the acoustics. And that actually has the property of the susceptibility and other properties of the coal, which may actually be a marker for your defined thing. So we are actually trying to use that kind of. So this is one example. Second example, again, nanosensing. We wanted to detect everybody from breath, you want to detect diabetes. It's a very common thing. We talked to Dr. Mahan's diabetic lab. He told, no, it's not a problem that people actually, if you have a diabetic, you will put your insulin. It is not that difficult thing, people put their syringe. He told, I cannot detect pre-diabetes. That is a problem of India. Pre-diabetics at you, if you catch there, then you can prevent the diabetes. If you are already diabetic, you just manage it. Pre-diabetic, can you sense without putting a needle? So we started this project with IIT Kharagpur. So we use nanosensors. Nanomole level, can I detect acetone and ethylene, which are the markers in your breath of a diabetic reaction happening in your pre-diabetic. So we are now actually mapping it to HB1C. We are just in the verge of going into a trial for this. And as we understand that all this needs a lot of kind of intelligence to be built in to make sense out of it. Quantum sensing, and we are working with IIT Bombay. Again, very fascinating area that can we image a chip when it is powered? Can I image the current in the chip at a gate level? That's what quantum sensing can do. And the quantum sensing, the value is very interestingly, instead of, we know that quantum computing is coming, and then people tell it's not coming. We hear this, The reason is the quantum states are very fragile. What it is fragile to? It is fragile to gravitational forces and electromagnetic forces. So you cannot shield it. And then you need a lot of error correction and everything to make computers work. But think about it, because it is fragile, it is extremely sensitive to electric field, magnetic field and gravitation. So excellent sensors for this. Femto-Tesla level you can do. So future, most probably we are talking to Denmark, DTU Technical University. They think that you will be able to build MRI as a helmet. Every neuron is imaged. So it will completely change the health. But then the data that comes in there is a different data, a different list altogether. Every neuron can be imaged. Then what the use of current MRI? No use. So that jump is going to come now. But here, as I said, just quickly tell, because it's a different paradigm of how we are using AI for design of sensors. It's the inverse problem. Like, I think morning there was a DALL-E. So if you use DALL-E, you can give a character in, it gives the image out. Why? Because it trained on many images which had text descriptions. Think of antenna design. Antenna design is again the image, layout. What is the output? Output is the spectrum. Spectrum is nothing but a byte stream. If I train a lot of that with a DALL-E kind of a Gen AI, if I give spectrum in, it should draw me the antenna. And we are actually trying to do this for plasmonic design. Initial results are very, very kind of encouraging. So, then the other part is, I think, very important. We already talked about that. Again, the privacy and other things are very important. If you do this AI, we feel the one part of the AI has to be up to edge. It cannot go out of my network. The data cannot go. There are two reasons. One is the privacy. Second is when I need low latency systems. Factory. If I detect something within 100 milliseconds, I have to correct. I cannot depend on internet to do that. Now in edge, if I have very small devices, I see 64 GB, 4 GB, 320 KB, these are the kind of memory that you get in the edge device, microcontrollers. How do I fit AI in there? So what we have done, we have actually created an AI-driven tool to reduce models. Most of the models, AI models, are over parameterized. Okay, so just to give you an example, I give the analogy. I give you two equations, two unknowns. If I give you 10 equations, you can either solve it for 10 variables, you can still solve it for 2 variables. Today's AI is actually solving for 10. Who told that ChatGPT need to be 1 trillion? Because it's trained on so much data, so many parameters. So actually you can reduce the model size. We are getting evidence of that. And like 40 MB to 250 KB, we have reduced test amounts. This is a very interesting example of a customer of us who is a pesticide company. They are actually trying to create a tractor with a thing automatically. They have to detect weight, which is AI. And once they detect, they have to spray. All their system is detecting and spraying on the wrong because there's delay by the time tractor has moved. So it's a very hard real-time requirement. So can we do that? We're actually able to do that kind of a thing. So that is one part of it. And lastly, even that energy is not good enough. That thing, ultimately you have to go for low power. I think you've heard of it. AI is guzzling majority of the power. But our brain doesn't do that. Isn't it? Our brain is 20 watt. So there's a fundamental architectural problem in today's computing architecture. We all of us know about von Neumann architectures, where memory is outside, CPU is separate, and data is constantly moving back and forth. It was very good when you do traditional IT, logic programming, because I fetch the data, do a lot of things, then I give the data. What I do in AI? Millions of A into B plus C. Every ABC is in memory. So I am going back and forth so many times, that is generating the hits. That's why they are so hot, and if I don't know whether you know it, very recent result. OpenAI's OPEX on energy and cooling may be more than what they are earning on. So every time you give a query to ChatGPT, they are losing money on OPEX, energy cost. So there is a big area. So neuromorphic computing is a way to do it. I'm not going to go to delay, but very interesting area. It works like brain where it has a small memory and small compute co-located like a neuron, and it works on spikes, which is the chain, like in our brain also works on spikes. It doesn't work on the real data, chain in the data. So if we do that, is a spike data actually, where it works. So we use sparse data and use a different kind of a neural network called SNN, spiking neural network. There are chips coming out from Intel and coming out of, there's a Silicon Valley company work with brain chip, with whom we demonstrated in New York actually. And so this is a very interesting area, around 1000x less energy. That is the initial what we are doing. So I just promise that I'll just kind of conclude and talk about 3 application areas now. Technology, we talked about sensing and computing. One area what we are applying now is what we call as the intelligent multimodal perception. Bring all sensor data in. Can I have one model which can understand everything and create? We are working in a very, we are working on defense, we are working with police in India to create this complete, what we call as the intelligent command center. Let all data come in, image, video, telecom. Can a one model can handle everything, can do something, and then create actionable thing. First it can you predict, and then it can actually prescribe some actions to prevent it. So those are the kind of things that can happen. Healthcare, again, many things can be done. Only 2 things I talked about. One plus, we have actually created AI model now, which can now predict your heart block from your fingertip, pulse oximeter and ECG. We have trained the AI with the gold standard of the angio block, but now it is trying to replace the angio. The moment I replace the angio, this can be given to the head of the ASHA workers. Only oximeter and ECG. It will actually predict the heart block. It can actually tell you whom to go to the hospital. We are doing a 1,000 patient trial now with Cardiovascular Society of India. Hopefully it will, if it comes, then we'll know whether it works or not. It works on the US data, just to work on Indian data, that's the problem. And similarly, I think that's one thing. And this is my last slide. So, any very interesting non-clinical application, how do you evaluate advertisement? Ad is a $10 billion, $20 billion industry. It all rides on testing of an ad. Happens by they show the ad to some 100 odd people. They see it and then they fill up a questionnaire. Based on the questionnaire, they decide whether the ad is good or bad or change it, and based on that, you put it in the market. And that has around 13 to 23% accuracy. So what we are trying to do, can I now use your gaze? And then we have actually created a patented measure of attention, called what we call as blink rate variability. You will understand. When you are attentive, your eye blink will actually become irregular. We are using that, and you can see this. These 2 are ads from Ganesh. Actually, in these, the attentions are actually quite regular. These are our kind of measures in our algorithm. There, the attention is pretty bad. But point is, this was one of the top performing ad of Ganesh. This was one of the worst. But they never found out by that questionnaire testing. So now, if we get this tool ahead to the content makers, they can actually make better ads. So that's the idea that we are trying to do that. So I think this was covered by us, and I'll just end it. Thank you.
So I want to begin by sort of setting the context by saying what cryptographic proofs are. So cryptographic proofs are interactive protocols between a party called a prover who wants to convince the verifier about the truth of a statement, but without revealing any of the secrets involved in the computation. So just like regular proofs, we want our cryptographic proofs to be complete and sound. But in addition, we get 2 other interesting cryptographic properties called zero knowledge and succinctness. Zero knowledge says that a cheating verifier cannot learn anything more than the truth of the statement by participating in the protocol. For example, here W is the secret of the prover that is involved in the computation, and the verifier learns nothing about W other than the output of the computation. And the second interesting property is what is called succinctness, which says that verification runs in time logarithmic in the size of the computation. So essentially what we get is an exponential gap between performing this original computation versus verifying that the computation was done correctly. So the motivation is that such succinct zero-knowledge proofs have plenty of applications in decentralized systems because they essentially give us privacy-preserving proofs of computation integrity. That is, you can prove that a computation was done correctly, but without revealing any secrets and in a way such that verification is much more efficient than performing the original computation. However, the line of works I'm going to talk about is going to address certain gaps in these works. The first one is that it does not quite capture the realistic execution environments where multiple proofs are done together. And secondly, they are typically optimized for very specific intermediate representations of computations and therefore are inefficient for composite computations that show up in practice. So we are going to address these gaps between theory and the deployment expectations of proof systems, and I'll talk about both of these issues briefly. We'll begin with realistic security models. So what do I mean by realistic security models? Let us think about a prover who is going to produce a proof of correct computation. Soundness only guarantees that this prover cannot convince a verifier of a false statement. But if we think about what this prover is doing in the real world, the prover, for example, has access to a public ledger where the prover can see publicly available instance proof pairs. And after seeing all of these instance proof pairs, the prover is going to sort of mall these proofs together or combine them in arbitrary ways in order to produce a new instance and proof in a way such that, either this instance is false or it does not actually know the witness corresponding to this instance. So this shows that the soundness guarantee used in traditional proof systems does not quite suffice in realistic applications because of this malleability property that proofs can have. So what we need is to capture this non-malleability, and this is what we do in a bunch of recent works where we augment the power of the adversarial prover by providing these oracles that the prover can actually see in realistic environments, and then guarantee that even in the presence of these powerful oracles, the prover cannot break soundness and convince the verifier of false statements. And the second realistic model is that of composition, where typical cryptographic protocols are proven to have standalone security. And what happens is these protocols are rarely used as standalone objects. Instead, they are used in larger secure computation protocols, and these security proofs break down during this composition. So what we need is not just standalone security, instead what is called composable security that guarantees that security of protocols hold even when they are done arbitrarily together in larger environments. So we provide a compiler that sort of takes a proof system that has standalone security guarantees and lifts it into a proof system that has security even during composition while preserving all the desirable features like the succinctness and so on. The second issue about being applicable in real-world decentralized applications is that of efficiency. So here the problem is the following. Imagine we have a large composite computation that is a conjunction of two subcomputations. And one of them is an algebraic computation, which means it is natively represented as algebraic computations. And the second is natively Boolean in the sense that it has a very efficient Boolean circuit that captures this computation. And both of these subcomputations share part of the input that is represented by W here. So most proof systems are optimized for either algebraic or Boolean computations. And if one has to prove this larger computation, the way to do it is to homogenize the entire computation by either writing the algebraic part as a Boolean circuit or expressing the Boolean circuit as an algebraic computation and thereby incurring overheads that worsens the efficiency of the system. Ideally, what we would want to do is use a proof system that is customized for the algebraic part, use a proof system that is customized for the Boolean part, and still guarantee that this shared input W here is indeed consistent in the two proof systems. So here we contribute to a line of works that is called the commit and proof paradigm, where the high-level idea is that we are going to commit to this shared input W and then use different proof systems together with very efficient linking proofs that can link them together And this commit and prove framework has implications where you can break down a large heterogeneous computation into multiple subcomputations, use different proof systems that are efficient for each of them and tie them all together without violating soundness and keeping the efficiency that each of these proof systems have for that respective subcomputation representations. So one application here is proving that a public ML model was trained on some sensitive but authenticated data. So many speakers here today talked about responsible AI, biases in AI and so on. And I want to point out that such efficient proof systems can be used to overcome a lot of these problems. For example, let us say I have this public model and I want to prove that it was trained on data that is authenticated by some authority. Of course, it is sensitive data, so I cannot simply reveal it to you. But what we can do is publish a short commitment to the sensitive database and then use the kind of cryptographic proofs I've talked about to prove that this database is digitally signed by a public authority that everybody trusts, and then go on and produce proofs that whatever inferences you're getting is indeed from this model that was trained on this committed and signed database. Of course, it has applications beyond machine learning, but for now, let's discuss it. The second point about efficiency is that most of these proof systems address computations that are represented as arithmetic circuits over a finite field, which means that we think about addition rates and multiplication rates over a prime field F. And again, what this fails to capture is that a lot of CPU computations are computations that are modulo 2 to the 32 or 2 to the 64 and do not quite match this prime field model. So what we do in this line of work is come up with zero-knowledge succinct arguments for native arithmetic over general rings that are not necessarily fields. And one application this allows us to do is have verifiable outsourcing of computation on encrypted data. So what does this mean? So here we have a light client who cannot perform a heavy computation. Again, think about running a training algorithm of a machine learning model. This is heavy computation that this light client cannot perform.
Actually, the microphone, the sensor, I mean the problem in the sensor can change its location. But your hair is hitting this microphone. So you have to change that.
Yeah. So what we can do here is have this light client outsource the computation to a powerful server. So this is something we already do. However, for privacy reasons, we don't want to simply give out the plain data to the untrusted server. So instead, what we do is use what is called a fully homomorphic encryption scheme to encrypt the data and then have the server compute all the encrypted data and return the output of the function that can be locally decrypted by the client. However, this kind of solutions based on homomorphic encryption falls short of the following, where the server is untrusted for privacy but trusted for integrity. So ideally what we want to do is, because this is untrusted cloud, we don't want to trust the cloud for privacy or integrity. That is, if I don't want to give my data to the cloud because I don't trust this entity, there is no reason for me to trust this entity to do the correct computation. Right? So what is the guarantee that this cloud is actually running this computation F that I want it to run? It can return any arbitrary function. In particular, it can be lazy and simply return constant, and the client will have no idea. So what we will need here is not just a fully homomorphic encryption, but a cryptographic proof of correctness that the server can attach. And not only will the client now decrypt the output, but it's first going to verify proof of correctness. And if it indeed holds, the client is going to decrypt the output. Okay, so I am running out of time, so I'm going to just take a minute to talk about one last efficiency concern, which is that about memory addressing. So one application here is that of blockchain rollups, where we have what is called a layer 2 chain, where we want to bunch a lot of transactions that change the layer 2 state into one transaction that is updated on the main chain. So the advantage of such a roll-up idea is that now there is a very small computation that is about verifying the proof on the main chain, where a lot of the hard work is going on off-chain in the L2 chain that need not be done by the verifiers. So this gives us both verification efficiency and also smaller costs in terms of transaction gas and so on. So cryptographic proofs can also be applied here to get very scalable and roll-up solutions to scale our blockchains. So I'm going to stop here and say that there are a bunch of applications of cryptographic proofs, starting from roll-up, privacy-preserving proofs of solvency, to verifiable outsourced computation, and they are the key drivers of true scalability and privacy-preserving decentralization. Thank you.
That's image in front of you, or a couple of images in front of you, and you can just tell what's the image of. What's this image of? Yes, thank you. So many of you probably have come to Bangalore through this place the day before yesterday or yesterday. So that's correct. And what's this image of? Okay, great. People know about IS. So these are special type of images. Can any one of you can tell what is this image or what is the type of the image? Anyone?
Afternoon.
So looks like people are not doing Instagram live nowadays. So these are called these images are called something like Ghibli images. Have you heard of this term, Ghibli images? No. Okay. This was a recent Instagram trend where you can put any images in ChatGPT or any of the agentic AI platform and tell that Ghiblify this image, then you will get this kind of special effect images, right? And all of, as many of the talk already discussed about ChatGPT or any other AI platform, that this ChatGPT applications are good. Yes, this is an online solution to almost everything. Yeah. Earlier we used to Google, nowadays we used to just tell that, hey, I have this fever, am I getting cancer? That we put in ChatGPT. Yes, it's an online solution of everything, we are all amazed. But are there any drawbacks? Yes, there are many drawbacks like privacy and security, but I will talk about one of the prominent drawbacks of all this agentic AI platform. So many of you know the algorithms which are powering this ChatGPT or any other agentic AI platform are like transformer-based network. And these algorithms are actually using a lot of GPUs. Like OpenAI has maybe thousands of GPUs which are, I don't know, on the sea or somewhere, which are powering these ChatGPT applications. And there was an article that the average power consumption by ChatGPT in January 23, when this application came to the public, and just for inference, it's not for training and everything, was between 11 lakhs to 233 lakhs kilowatt hour. That's equivalent of power consumption of 1.7 lakhs of people. If we go further down, that is also equivalent to a carbon footprint of 25 kilograms of carbon dioxide every day, which is similar to cutting down 406 trees every day. ChatGPT told me that Bengaluru has 22,000 trees, and it will just take less than 2 months to cut down all the trees in this particular campus. And don't quote me, don't come after 2 months and tell me that, hey, the trees are already there. No. So my bottom line is, these applications are great, but they are taking too much of energy. And I will tell you briefly why are they taking too much of energy. All of us use computer, all of us use mobile phones, and all of you know that there is a separate memory as well as compute. If you take your computer and then open the backup, you will see that there is a processor and then there is a separate memory. Now, whenever you launch any of these machine learning applications, they have huge number of weights. They generate huge number of data. Those data need to go to the memory and then again need to be fetched back and forth. Like one of the presenter already told that there is a lot of redundant data communication, data movement. Now, unfortunately, in the last 20 years, the computers and technology have been evolved a lot. But this communication bandwidth or the interconnect bandwidth, which is connecting the compute part and the memory part, they have not been evolved like the computers have been evolved. So that's why you can see that at the end of 2023 or 2022, there's a huge gap between the compute and the memory as well as the interconnect. Now, in our group, we address this gap by using the technology called in-memory computing. Specifically, we use analog in-memory computing and we are investigating how we can use this technology to accelerate some of the relevant applications. I'll give you a very brief overview how this analog in-memory computing works. As the name suggests, the compute is embedded on the memory. We don't need a separate memory as well as a separate compute unit. So I hope all of you know the Ohm's law, V is equal to IR, right? So you can see that there are two resistors in this figure. The conductance of the resistors are denoted by G1 and G2. So the conductance is nothing but the inverse of resistance. Now if you apply a voltage of V1 across the resistor whose conductance is G1, then you will get a current I1 equals to V1 G1. And if you apply a voltage of V2 across the resistor whose conductance is G2, then you will get a current I2 equals to V2 G2. Since these two resistors are in series, the total current will be I1 plus I2, which is nothing but V1 G1 plus V2 G2. Now what did we do here? We actually took four numbers, V1, G1, V2, G2. We multiplied V1 G1, we multiplied V2 G2, and then we took the sum, V1 G1 plus V2 G2. And that is nothing but multiply and accumulate, which is a very, very repetitive operation in any of the machine learning application. So if we can integrate these devices in this crossbar array, then we can get a vector matrix multiplication operation done. Now, when you are talking about this in-memory computing devices, they are not simple metal resistors. There are special semiconductor devices whose conductance can be changed if you change the bias voltage. Again, bias voltage is different than these voltages. That means you can think the conductance can be represented as weights of the machine learning application. So weights can be embedded onto your processor, and then you can flow the activations. Due to the property of the devices, the output activations will be computed automatically. We are investigating how machine learning applications can be accelerated with these kind of devices. On top of that, we also use something called chiplet-based integration. Nowadays, again, if you open up your laptop, if you are using a laptop with Intel processor, then you will see a chip where it is written Intel Core i7 written on it. But as our application demand is increasing day by day, the chip size is also increasing, and if the chip size increases, the defect increases, so the fabrication cost increases. Now, to address that limitation, there is a new technology called 2.5D technology or chiplet-based technology, where instead of a single monolithic chip, you have multiple chiplets on the same package, so that each chiplet size is less, but you get the same functionality. We are seeing how this chiplet technology, along with the in-memory technology, in-memory computing technology, can accelerate the relevant applications. This is a high-level overview of our proposed architecture, where you can see that some of the chiplets are of in-memory computing, and some of the chiplets are of the CMOS, the traditional TPU-based technology. So we have evaluated our proposed architecture, and then we compare the latency as well as energy consumption with respect to NVIDIA Jetson devices. So NVIDIA Jetson is a very, very popular device which is used for edge applications. Now, as you can see, the different bars are showing the improvement in latency as well as energy for different LLM applications. So BT is basic transformer, which was proposed in Srinivasan's paper, and BERT is, I hope many of you know about BERT applications, BERT algorithms. So as you can see that, and remember the y-axis is in log scale. So you can see that our proposed architecture have huge potential, and it can deliver up to 972 times improvement in latency and 1600 times improvement in energy. Of course, ours is a simulation based method, means we just simulated our proposed architecture, and Jetson is a real silicon device. But what I am trying to say that this in-memory computing technology, as this 2.5D technology, has an extreme potential to accelerate these machine learning applications. And again, these technology are the in-memory computing technology which I am talking about is not productized yet. Maybe it will come in the market 5 years, 10 years down the line. It's still in R&D by different like computing company giants like Qualcomm, Samsung, etc. Now moving forward, we are also proposing a 5.5D system, because as I was saying, that chiplet-based technology is there. But again, if we need more chiplet, then your package area increases. That is one problem. Another problem is chiplet to chiplet communication is expensive. That is also energy consuming. That is not only energy consuming, that communication is slow. Now, to address that, we can vertically integrate. That means we can have one chip on top of each other, and there is a technology called through silicon via, which will connect different planes of those chips, and then we can have those 3D stack modules replicated on a package to make a 5.5D structure. Again, 5.5D is a
like imaginary name, which is nothing but 3D plus 2.5D. So that is one of the technology we are working on. And again, if we propose a new device, we have to propose a software. Today, NVIDIA is NVIDIA because they have CUDA, right? Like the other companies, I hope people are not there from these companies, which I'm going to take the names of. The other companies like Intel, AMD, they also have their GPUs. But why didn't they catch up as NVIDIA took the market? Because they didn't thought about the software. They didn't think about the software. So that's why we are also proposing a specific programming model, which is useful for this analog in-memory computing devices. Now, when we say programming model, at the end of the day, user want to use PyTorch, right? You want to do torch.nl so that you can instantiate one layer of the network. Similarly, we have built this library Succinct. Succinct stands for computing memory. If you do a Succinct.addLayer.mha, then it will instantiate a multi-headed attention layer. Similarly, you can instantiate a normalization layer, feed-forward layer, etc. Now, internally, it will create the data structure, then it will create the instruction sets, which in turn will create the microoperations, and these microoperations will be embedded or will be dumped onto the device through the drivers. So these two is our ongoing work, and that's the.
So good afternoon, everybody. I'm Manoj Jain, PMD BEL. Throughout my career, I was in R&D. Last 3-4 years only, I am so-called in the business domain, I should say. Bell was founded with this mission of Make in India. So this Make in India is not a new slogan. In Bell, we know when 1954 we were made, it was made to manufacture some defense electronics equipments in India. And that way our journey started. But over a period of time, it was not only just manufacturing. Manufacturing was a TOT from foreign OEMs and later on DRDO technologies. Later on we realized that it should be homegrown also. So it should be designed in India also. That's why we started Design in India concept, and we have large R&D base. But later on we realized that it is not only the product related R&D we have to do design or technology related R&D also, so that the products can be realized much faster. So that's why this Central Research Laboratory concept came in Bell in 1989, and we have scientists also in Bell. So we have engineers and scientists, a mix of both in Bell. So those scientists takes care of design, that also futuristic or proactive designs. So proactive technology development is done by CRS, and our other fellow makes it a product. And then finally production takes a real manufacturing in India concept. So that is our concept overall. But anyway, Government of India launched the Make in India for all sectors, including defense, in 2014 as a mission for making India manufacturing hub. That you all know, because earlier it was like a call center type of concept and other things. IT boom was taken in a slightly different way. In 2014 it was realized that until we are designing in or manufacturing in India, especially the hardware centric efforts started more focused in India after 2014 in all the sectors, including electronics mainly. But defense electronics primarily was made in India. Before that only, like Bell or HA and others. So it was mainly to encourage domestic production, attracting foreign investments, reducing dependency on imports in all the sectors. And of course, defense also is one of the sector. Because in the defense, although Bell was there in 1954, DRDO in 1958, but still the technology was so fast changing that we had for large platforms or large arms and ammunition, we were depending on foreign technology. And still it is there to some extent. But over a period of last 10 years, definitely we have gone a long way in defense manufacturing, defense designing, and overall things. So now I think more than 75% of the order comes to Indian companies only. So Indian production is now reached in defense 75% and above. So anyway, there were so many reforms to be done for this Make in India concept. Mainly ease of doing business. So many procedures were made simpler in defense also, and overall in all other sectors. This public procurement preference to Make in India 2017 stipulates that mandate will be there for domestically manufactured. And later on, defense went one step further. That in defense, it was told minimum 50%. Then last year it was made to 75% procurement from India. In that corridors, the two industrial corridors for defense came up, one in Tamil Nadu and one in Uttar Pradesh. So these two are very, very important because now in this much more focused attempt is done, other than like earlier it was Bangalore, Hyderabad, mainly these two for the defense. Then overall it was told for balancing out overall regional balance also, these two came very, very important industrial corridors for manufacturing defense products, and a lot of schemes are there for investments in that. And overall, so many other concepts were there in this, including financial support for manufacturing units, etc., startups, related facility by government, and government told all the PSU also to take care of all these things. I just will touch upon this little bit more only. And so many things for skill development and innovation related things. The most important which we as well also took part in HAL is this third one, the DIO, Defense Innovation Organization, where you all may be knowing a little bit that this one is the one largest innovation program in defense, maybe largest in the world. Because we have seen so many other countries also, including US, this type of structured program, although it is started in a slightly unstructured way, but it has become now totally structured program, and more than 1,000 crore already is invested. The government has allocated. It is not only government, it is actually started with BEL and HAL. We funded around 50 crore to offer up this, and we are the founding board members for DIO. And then later on, other PSU also have contributed, DPSU. And I think government has given around 500 crore, mainly for Aditi scheme. The main IDEX scheme is mainly managed by the funds of DPSU, and Aditi scheme funds are given by Government of India. Right. Why it is successful program? In this program, handholding is done not only by the users, but PSUs and overall MOD, and to see that these startups develop that niche technology for defense and see that they get order also. Till I think last month, around 2,100 crore worth of contracts were signed with the startups. So means at least this much business already has accrued out of this startup concept, which started 2018. And you know, first 2-3 years it was just stabilization phase itself, and from that it has migrated to more than 400-500 challenges are right now there, and they are being executed through DISC 1, 2, 3 like that. I think till DISC 13 are there already. So it is well established process now, and well is proud to be associated with this journey of startups, because we are not only founding member, we are a part of the evaluation committee and handholding these startups to do that. GEM anyway is there now for almost all procurements etc. are done through GEM. Then the role of MSME started increasing in defense, and anyway Government of India mandated this 25% minimum procurement from MSMEs for all the PSUs. So that is also very much good initiative. Like this type of policy reforms are very much required for sustenance. Otherwise we will keep on talking, yeah, good, MSME is good, we will work with them, we support them, but support them in a business sense. But that also is very much required. It is not only verbal service to them, it is actual business engagement to them. So they are part of now the larger ecosystem of all of us. So we have almost 4,000 plus MSMEs specialized for our type of working. Overall 16,000 plus we have vendor base. So in that 4,000 plus are categorized as MSMEs. So we have been encouraging all these things for MSMEs. Then came the DAP's defense procurement process that is very much quantified and very much supporting now Make in India. And you know, the most important way of procurement nowadays is by IDDM. Means indigenously designed, developed and manufactured. Any product, if the Ministry of Defence has to procure, or any defence user has to procure, they will firstly see whether it can be classified under this, whether the technology is already available in India or designed in India. Then they are procured through IDDM path only. If not, then only there are various routes of buy and makes. But first and most important is this. And most of the strategic programs nowadays are through this buy IDDM category. Whether it is QRSAM type of missile program, arms and ammunition related systems, LCA type of system, MCA, now they all qualify under IDDM category. So most of the procurement is done through IDDM category. Then there are definitely Make 1 and Make 2. They are the two main funding patterns for designing, where funding is done by Government of India. So in Make 1, it started with 90% funding by MOD, but now it is 70% only. And this is mainly for high risk technology intensive projects where government feels industry or individual cannot invest. So there government is ready to invest, but it's limited to 70%, but at least order is guaranteed. So various programs are going through this Make 1 path right now. But that came Make 2. In Make 2 this is industry funded. So although off the record I can tell you it is not a very successful model, because industry has to fund. If it is 1 crore, 2 crore, okay. But if it is requires much more, and most of the program, government and including DPSU started in Make 2 mode. Even we also have our own Make 1 and Make 2. So Make 2 mode, we will also again ask a small industry to invest. And once it is certified, once the prototype is ready, then only I will procure. But what if prototype fails? What if any other challenges comes during that phase? So that industry cannot sustain, especially for defense products. So in general, Make 2 started as a good initiative, but over a period of time it has to replace by Make 1 or some collaborative R&D mode for larger programs. For small programs, Make 2 still is attractive, and it is one of the way of developing products in India. Then came this concept of positive indigenization list, which clearly tells these items I will only take after some time only from Indian companies. Not at all I will import these products, systems or subsystems. What we did overall. So anyway, we have indigenization vertical. Separately we have created. So we have a PDIC, Product Development and Innovation Center, that is mainly for innovation and indigenization. So we created a separate vertical for indigenization, because indigenization is not only done by us alone, like we have our own 3-tier R&D that is doing indigenization, but we have to take this larger ecosystem of MSMEs, startups and others as part of our indigenization journey. So for that we have created this vertical where we are periodically interacting with all, including ministry. Monthly reviews are there, and any industry can approach us. Most of the indigenization items, now I think it is 100% of items which we are importing are already put in this Trojan portal with all the point of details, basic details are there in that, what these items are, what type of quantities are required, etc. for this. And then we conduct various type of events, etc. to involve MSMEs, etc. for our this type of development programs. So indigenization is nothing but R&D. They are the research and development program, but done jointly with the help of industry. So we have various things. We have display cells, we have nodal officers for each and every SBU level, and for each and every item which is there in present portal, we have that. And we have opened up our facilities also for MSME and startups, because the way to indigenize is to collaborate with others. So for that, so many other schemes we have done. We are having 350 plus partners for collaborative R&D. Then this DTI is also a very good scheme, Defense Testing Infrastructure Scheme, where in the 2 defense corridors, 7 facilities are being created, partially funded by DPSU, partially by Government of India. And these facilities more or less going to be inaugurated in next few months. Almost 400 crore worth of investment is done jointly by government and by DPSUs in these facilities. So their MSME and others can come and start testing, and they will be Section 8 companies, so no profit, not for profit type of way it will be running. and give this type of a testing infrastructure for all. Because in the defense, testing and certification takes most of the resources or time and money. So that type of thing is being created where we are there. And we are working with almost all educational institutions to leverage on the basic research, then convert it into a product-oriented research. Collaboration with the IISc just mentioned, actually once we mentioned IIT, like morning also it was told, IISc is generally excluded from the calculation of academic institutions of IITs. So anyway, that's why we also have written that IISc also we are working very, very closely on AI related activities, all other activities we are tapping. IDEX, so I have already told you, and then other activities which we are doing. So what we have to do, what way we can support our MSME and other companies in this. This was the items, we have to declare how many items we are indigenizing minimum, and then it is monitored, and then how much savings we have done by these items by ourselves. So these are targets. Some statistics are there. These are the PILs. There are two PILs. One is the main PIL at system level by Government of India, PIL 1, 2, 3, 4, 5. And then DPSU also have their own PILs. These items I want to only take from Indian companies. And so there is a long list of all these items and items how they are indigenized, how they are going to be indigenized. So good progress is done in total indigenization related activities by all DPSUs, including BEL. We have taken up so many projects under Make 2 of Armed Forces also, where we are funding to develop critical technologies related to arms ammunition, drones, so many things where we are funding, but government is assuring once you complete, it will be implemented. One of the classic example of Make 2 EOIRST for Su-30, which is actually around, I'm not wrong, 150 crore worth of investment HAL and BEL jointly are doing. With no assurance of Government of India, not a single rupee they are giving, and it is quite challenging. Including even foreigners told in this money and this time frame they cannot do, that's why they are not interested in even in working for joint development, etc. also for this. So these type of projects which are really technology and money intensive, although we are still running in Make 2. So some of the programs we thought let us, because this program is strategic nature, we invest for that program because we know that technology definitely will be used for this program, but even if we fail in meeting that specs, definitely byproducts will be used across various programs. So it is like an investment done. Just 2 more minutes, I will try to complete. This is also a new concept which we have done now. The AI as a buzzword came, so we started investing on AI, but we found the main bottleneck for AI is not servers, infrastructures, data. And data is available in case of defense by defense users. So why not create an environment, incubation center where we, user and startups, all the three can sit together and user is having access to data and create overall ecosystem and then develop that. So we have opened for Army, Indian Army AI Incubation Center, Indian Navy Incubation Center, these two are already done. Air Force Incubation Center also is in just pipeline now. So where we, startup and users are all sitting together and developing niche technologies for AI. Because that was the need of the hour, because otherwise we can develop very great algorithms of AI, but until we fine tune it or until we train it with a real data set, we can't. And real data set access right now is into user. Because we don't have that type of advanced systems which directly capture this data. Even if they capture the data cannot be given to designer. So that challenge we have just done. We have some 2 more concepts with TIF and STF, where again we are working dedicated with Navy and with startups. Where Navy selects a startup, that this startup has this particular niche technology, let BEL work with them. So BEL is funding and getting it developed, and once the product is developed, it will be purchased by the Navy. So a business model around that is made. And in first year of induction of this STF itself, we have come out with I think 5 great technology development through startups and a good business case for that. These are conclusions. So definitely BEL is aligned to Make in India. BEL was born with the concept of Make in India only. And we are committed for indigenous design, development, manufacturing of defense systems, either ourselves or through MSME and other collaborative R&D partners. We are continuously monitoring, taking part in all Make 1, Make 2, IDEX, PILs, and it has been closely monitored by Ministry of Defence. Almost monthly meetings at JS and above level happens for that. We are strengthening collaboration with almost all DRDOs, DPSUs, MSME, startups and academia. Almost all IITs we are having running projects. And we are promoting technology absorption, innovation and capability enhancement across our supply chain. So we are reaffirming our commitment to make in India a global hub for defense manufacturing. So that not only BEL, I am representing BEL, that's why I am telling, but all DPSU has been given this mandate and they all are working for that. And in addition also, large private companies in defense are also following now this principle. So we are working in a really collaborative way to develop indigenously almost all technology which are required for our defense forces. That is brief I wanted to just touch upon. I have not talked about technology or technical or my technical journey, I am sorry for that. It is mainly to give an overview about how indigenous technologies are critical for defense sector. Thank you.
Thank you.
The process is after 15. The bell is after 15 minutes.
Oh, well, also 15 minutes.
So my talk has two parts. I'll spend 5 minutes on the things that have already developed, just to give you a glimpse of what already has been developed. So there are 3-4 dense slides. Then I'll talk about the future, what we are working towards. In IIT Hyderabad, this whole effort of, we call it 5G and 6G, but it was just future wireless communications in general. 2011 is when it all started. Professor Desai gave me one fine day, just take this 15 crores, you have to build something. I said, I don't know how to build. He said, you have to build. That's how the conversation started. And there we are now, almost, a decade later. So mighty DOT, DST funded us very sustained, for a long period of time. Of course, CDOT also gave us some grant recently. We would have trained more than 1,500 people, all kinds of people, engineers, PhDs, over this long period of time. At any given time, we have about 200 people working with us in different capacities last several years. 300 patents have been filed, roughly half and half in the US, more than 100 has been granted. We built what are called claim charts to enforce these patents on global standards. For example, soon you'll probably see some enforcement on all devices, 5G devices. There are waveforms that that are used in this phone that you use. That will be enforced sooner or later. There are also some essential patents that read on to 4 aspects of what are called large-scale MIMO systems that go into base stations. We have pioneered that thanks to you will see that development a little bit later on how we went about it. As we stand today, a complete 5G system has been built, deployed, and it's going through, it's carrying live traffic, so we're in an expansion mode. This is something like what you see on the cell tower, the whole equipment. Radio, baseband, including the core, but we call it a chota core. This is a fixed wireless access core, not a TSP grade mobility core. We have 22 sites operational. One site in Nizam's hospital in Hyderabad is carrying live traffic. Soon 2 villages will do a blanket coverage of fixed wireless access through Telangana state and Nike. We have a chip called narrowband AVT. It's actually a narrowband SDR. It practically can do anything, any waveform that is below 200 kilowatts bandwidth, you can synthesize, transmit. Today we're doing narrowband transmission of 3GPP standard. It's a technology that is very high TRL. We're going to release the applications very soon. The SoC module ready. It's TSMC 40 nanometer, very long battery life, low bit rate communication. It is tested with L-band geosynchronous satellites. There will be a transmission with Viasat and BSNL soon. So we'll introduce both terrestrial and satellite devices. So this is an example of what this is the standard cell site equipment, radios, antennas. But there is one antenna panel you see. It's a very advanced 192 elements, 32 channel transmit receive massive MMO. It's deployed right now commercially along with the baseband that sits in it. A full-blown massive memory system is already deployed. It's something that competes with the best-in-class current products out there. Okay? And most of it is thankfully is upgradable to 6G because in legacy bands below 4 GHz, 5G is going to stay and 6G will be a minor upgrade. And then the way 6G will be built is that it's for new frequency band between 6 to 7, 8, 9 up to 13 GHz. So a lot of it will be, the core will be reused and then there will be RF upgrades into 6G. We'll talk about that. So this is the left side is the analog portion of the SoC. The right side is digital, you can't see much. This is a module. The chip is 13 square TSMC 40 nanometer. In mass production, it comes under under $2. Hopefully more close to $1. And the whole module comes under maybe 500 rupees to 700 rupees. And it connects to anywhere, anytime, anywhere in the world because it is satellite compliant. Now I'll move on to the second part of this. This is more futuristic, more what we are going to do or what we are doing rather. ITU defines this timeline starting from 2020 to 2030 because 5G is something that is closed at 2020 from ITU perspective. And 2020 new program started and it ends in 2030. It's called IMT 2030. That's also known as 6G. We have done some work in this. We are somewhat at the midpoint now. In next 2 years, you'll practically see the full contours of 6G, well defined, and we'll probably put some prototypes and even field deployments in the next 24 months. So this is the diagram you'll see if you are trying to, if you Google 6G maybe, not Google, but maybe if you do a AI search on 6G, you'll see this diagram. The interesting part is that 5G is in the middle. So it's a part and parcel of 6G. So the middle portion is 5G. There's 3 vertices. And then there's new dots added. They have new stuff like, what is new here? Oh, integrated AI and communication. We can have maybe a coffee conversation about what is this AI in communication, but it's there. We introduced the India flag, ubiquitous connectivity. Normally, in an ITU setting, a country like India doesn't even get a voice, let alone introduce and define what 6G should look like. So this little dot, we introduced it in ITU, that actually took an engagement between the US and India administration to resolve a dispute that we wanted this, the rest of the world didn't want it, there was a big fight and it was resolved with the direct intervention at the highest levels. So we got a seat at the table, we were able to influence this whole evolution at the very core of things. We also introduced in as ITU 2 new elements. This green stuff is 5G, this blue is 6G. These are what are called TPRs, technical performance requirements. You'll see latency, data rate, spectral efficiency, things like that. But we introduced something new there called coverage. People resisted a lot to say, oh, coverage is not something we define. It just, you do it. It's not defined. So there are a lot of pushback on that, but we got this thing in codified. Interoperability. Satish is sitting there, chairman TSDSL. He said, I want interoperability. That is interoperability between different subsystems of the radio, like a baseband and radio, they interoperate using open interfaces. They call it open RAN, but in general, interoperability. Surprisingly, he was asking me, I was like, you pushed it last day, last minute, this got accepted. UK tried 2 years unsuccessfully, but 3 days of work we were able to convince and got this in. Of course, the vendors did want to introduce interoperability in 6G for various reasons. So Open RAN was done in 5G, but it's going to be stay. AT&T and Ericsson and others have already upgraded the North American network to Open RAN interface compliant, and 6G will have interfaces, open interfaces. That is, the baseband and the radio will be split in a very non-trivial manner. Okay, a little bit more into deep dive into the research. We love waveforms. We introduced some in these phones. They're part of 5G and the early discussions 3GPP. There is what is called a study item ongoing now that will happen for next 12 months or so. Some early decisions have been made. We introduced, what we introduced in 5G kind of is preserved in 6G in the most fundamental manner. So that uplink of 5G introduced has two waveforms. OFDM and DFT-SOFDM. DFT-SOFDM is something like a single guided system, somewhat related. In the DFT-SOFDM family, we introduced a completely new transmission mode in 5G called pi-half PPS scale with spectrum shaping, a data channel, control channel, MIMO, reference signals, all sorts of things. They're all part of the phone mandatory. And that will get carried over to 6G because these are core 5G features, they just get carried over. We did want to introduce something new in 6G in the downlink. I have not been very successful at that, but we'll see maybe at some point in time in the next 2-3 years. We wanted to introduce the DFT-SOFDM low PAPR transmission, reduce the energy consumption of the base station by 30-40%, increase the range, but people said, oh, don't decrease the cost of the base station, people won't make money. So, I kind of gave up. There are still discussions, but it's a hard sell. But we will probably do it for defense, somebody else later on. We have a new waveform I'll talk about. We did a decade of research on extremely large antenna arrays. That's when Prof. Desai gave me this 18 crores in 2011. Said we build something, cloud RAN, massive MIMO, distributed MIMO. I said, it cannot be built. Push. We finally built it. We built massive MIMO, cloud RAN, distributed MIMO. Experimentally, we built them for a decade. Today, you saw the antenna array. It's commercial, it's deployed. It took us a decade to do that, but it looked like something like this when we did this. It's a mega gigantic array with lots of hardware. Now it's all in a single box, by the way. It's a 2.6 GHz system, and we put all these dividers in azimuth elevation. We did a crazy set of experiments spanning many years. This is one MU MIMO transmission over a 30-degree sector, and we showcased that you could get something like 100 bits per second per hertz in 360 degrees. It's like unthinkable. GSM was 0.25 bits per second per hertz. That's like 30 years ago.
Another agreement.
Yeah, we have done that. So we introduced something new. We have a new waveform. You have TDMA, you have OFDM, you have DFT spread OFDM. We created something new. It's not really new, but it's very old, but it's also very much new. We did TDMA, we did OFDM, and we fused them in the OFDM family of waveforms. So the rightmost side is OFDM, and the leftmost side is the DFT-SOFDM. Even further to the left, we did time multiplexing of reference signals data in a very short time, what is called OFDM symbol. So essentially, you create a OFDM symbol, you put reference signal data on one OFDM symbol. The transmission time can be, let's say, 10 microseconds, and you transmit all the information you want, control, data, sync, everything in 10 microseconds. It's immune to download because it's so short, and you can still equalize it using lots of DFTs, FFTs, and all that. And it can also have low PAPR because it belongs to that family of DFT spread OFDM family, and we play some more trick, and we can get at some point we can transmit the signal close to PS saturation. Don't reach very long distance. That's the pi-half PPS scale mode. But nevertheless, it goes all the way to 256 QAM. This is what I want to push in 6G in the downlink in the base stations. Maybe a part of it will be introduced, but we'll see. It's going to be hard, but in the uplink it's already there. In 5G, it's going to be there in 6G also. That's it. Lots of curves, results. The building China of relays. We have the SOC. This is an narrowband SOC. It's going into production. We'll probably have a broadband SOC maybe in a couple of years. That's something I'm working on. Base stations we built, but I am trying to build something like what's there in the phone. It's on an FPGA already. The Qualcomm chip that we have. We already built an FPGA prototype. It's connecting to the Geo network, Gator network. But we want to harden them into a full SOC, fully software defined. That's still some work. So we have a narrowband SDR, we'll have a wideband SDR, maybe another 3-4 years. That's where we have a base station network, we have an SDR. So you mix them, then you can create man nets, you can create defense communication systems. We are doing low altitude drone detection using the massive memory radios. We are seeing that as we speak. So what we started in 2011 as to fully indigenize as a paper study. 15 years down the line, we have these products. Hopefully, I can last another 10 years, then we have 100% indigenization by this time. Thank you.
When we use AI for healthcare applications, then actually instead of data science, there is need of science of data. So there is a need of actually to understand the system. So motivated by that, we have combined the signal processing and machine learning algorithms together and generated various intelligent systems to detect the disease at early stage. And such kind of systems, they have a lot of applications. In rural areas, we don't have doctors. Such systems can detect disease at initial stage. And in urban areas, these systems can help doctors, radiologists to assist them to perform efficient diagnosis. So there is a lot of interest in the literature. So this is the overview of this talk. First we will see introduction, then motivation. After that, empirical decomposition that actually recently proposed signal processing algorithm, which does not need design of the basis functions. And then it's improved by the empirical weighted transform that we have proposed multivariate empirical weighted transform that will be explained. And then we will see its application for detection of epilepsy from EEG signals. In the end, conclusion will be provided. So this is actually one of the part of our work. This is actually fundamental problem, like when you have biomedical signals in your hand and you want to understand, there are a lot of information how to do that. And Fourier actually in 1807, he has suggested use of sinusoidal functions. You can represent this signal, this is unknown, in terms of non-functions, and then actually you can get the desired information in terms of frequency. So that was representation of the signal in terms of sinusoidal functions. And in real life, there are many types of signals. One of the classification is stationary non-stationary signals. And when you apply Fourier transform for this stationary signal, non-stationary signal, then you can see that it gives the same spectrum. So this is one of the major limitations of the Fourier transform. When you are applying stationary non-stationary both cases, it is not able to give the different spectrum. So motivated by that limitation, there has been actually a lot of work in the literature, and at this point of time, there are two directions. One is fixed basis function design. So we represent signal in terms of basis functions which man-made design from our side, like sinusoidal function, wavelet transform, etc. This new direction has come from 1998. Now, instead of designing basis functions, we extract them from the signal itself. So that instead of using mathematical formulation, we develop algorithms to obtain such basis functions. So in all these two directions, this is the motivation. Instead of sinusoidal function, we want to have time varying sinusoids, so its parameters again and frequency are changing with time. And then this model is suitable for narrow band signal, and then multi-component signals like wideband signals can be represented such kind of mathematical model. Now our talk is actually focused. This work is for multi-channel data. Like now this can be generalized. This can be considered like multi-channel data where each channel has narrow band nature. And this here, this is actually multi-channel data where each channel has multi-component wideband nature. So this is actually talk in this model is for our interest for this talk. And most of the signal processing algorithms in the literature, they are actually based on a single channel processing, and we have actually extended them for multi-channel processing. What is the motivation? If you see real life, there are many scenarios where we have multi-channel data. So first is like this here for diagnosis we record vibration data, that is multi-channel data. EEG signal recording from the brain based on multi-channel electrodes. ECG signals actually based on the multiple reads. So in all these cases, if you process the data individually, then they actually ignores mutual information and correlates with the channels. And also when you apply adaptive signal decomposition technique, then each channel will have different number of component basis functions. So mode alignment property is not preserved. So due to that, actually there is a lot of interest in the literature to come up with the multi-channel signal processing algorithms which will preserve model alignment property and suitable to multi-channel data. So this empirical mode decomposition, which was proposed in 1998, it doesn't need design of basis functions, just actually in a form of algorithm we apply. It has come from computer science background, and just based on the algorithm you decompose in the form of basis functions. So you don't need to design basis function, you don't need to know the nature of the signals which you are analyzing, whether it's non-linear, non-stationary, whatever data you have, you apply this method to decompose it into a certain number of components. So in literature it has been shown that this kind of decomposition is similar to the equivalent kind of decomposition. So you have approximately a kind of these subbands. Based on this concept, many multivariate signal approaches have been proposed in the literature, like complex EMD, rotation inverted complex EMD, bivariate EMD, multivariate EMD. And this EMD method actually has certain limitations, like empirical in nature, and also it has more mixing problem. So motivated by that, recently empirical Weber transform has been proposed, and it overcomes these two limitations. So in this actually research, in part of our work, we have detected epilepsy from EEG signals. So here you can see the human brain. This has 4 lobes: frontal lobe, parietal lobe, occipital lobe, and temporal lobe. And whatever you do directly or indirectly, everything actually affects one of these lobes. So this electrical activity, to measure one of these 4 lobes, we use electrode cap, and then these EEG signals are recorded from these electrodes. And for just an example, 2-channel EEG signal is shown. This is actually just for example. So in the literature, researchers they do this channel-wise processing, but in our work we use multi-channel signal processing. So this empirical wavelet transform, that is already I mentioned, it is based on the limitations of the EMD method. It has 3 basic steps. It obtains the spectrum, and then it segments it, and then it defines the empirical wavelet basis functions to separate out these components. And we have extended this empirical wavelet transform method for multivariate signals, and then we have proposed time frequency representation of this multivariate signal using EWT and its application for epileptic sedative. So if you apply this empirical wavelet transform to each channel, then each channel will have different spectrum, different boundaries, and different number of components. So model alignment property is not preserved. So what we suggested use of average spectrum from the all channels spectrum and average out, and based on this spectrum we can design this boundaries, and based on the boundary we design the filters and then separate all the components. And then we apply Hilbert transform algorithm to compute steadiness, amplitude, and frequency. And then we obtain joint distance and frequency and amplitude from these all channels for particular frequency component. And then we have extended this for all frequency component present in the signal. So that we call multivariate time frequency impedance. So like instead of single channel time frequency impedance, you can get multi-channel time frequency impedance. Whenever you have epilepsy disease, if you go to hospital, doctors actually see the large amplitude of the waveforms and presence of the spikes. Motivated by this kind of actually phenomena, and we have suggested these features which are also based on the amplitude. So these are our proposed features: mean of the distant amplitude, mean monotonic absolute amplitude modulus change, variance of monotonic AM change, and this is our actually proposed epileptic signal detection algorithm. So it is like you have 23 channels. Then you selected 5 channels in order to do the compression complexity. Then you apply multivariate empirical wavelet transform, and each channel will include the same number of components. And then we determine distance, amplitude, and frequency of each mode. Then joint distance, amplitude, and frequency of each mode computed. Then we extract certain features, and then we apply some feature processing, and then classify, and will automatically classify into seizure and seizure-free classes. So this is like somebody driving a car and is going to have epilepsy. This method can predict epilepsy in advance. Then actually you can bypass the epilepsy attack, you can take the epilepsy drugs. So this is just one example based on our approach, multivariate time frequency representation. This is 5-channel seizure data, seizure EEG signal. This is 5-channel seizure free. So if you see our proposed time frequency representation, multivariate time frequency representation, it has all frequency component, low and high or. In case of seizure free, it has only low frequency component. So this can be used as a signature to detect the disease, whether you have epilepsy or not. So like it's very it's a very simple feature, and it can be used as a tool for computer-aided medical diagnosis of epilepsy. Just in the initial stage, one can see whether it is very serious, go to urban area or hospital for the timely treatment. If you see these features from all modes, from the like 3 proposed features, they are noisy. So what you suggested, actually use of moving average filtering, and then it actually enhances these features and improve the distribution to be seizure and seizure-free parts of these features. And then further, we have suggested hardware product. So if you multiply all of them together, higher will be higher, lower will be lower, and then we get joint feature vector. So that is actually one of the important finding in the from our group. That actually machine learning cannot do. So machine learning can do classification of seizure free, but it cannot tell you what time seizures are coming, what is the onset of the seizure, when it is happening, what is the severity of the seizure. So here you can see this is the raw EEG data, and doctors they see these EEG waveforms, and this is the onset of seizure, but it is not clear from this movie. When you do good signal processing and when you apply these proper features, then you can see this initial part, this seizure is initial. That time can be used to predict that it's making the alarm, so that person will know that he's going to have epileptic seizures. So this is actually very good history analysis interpretation. So in diagnosis, medical diagnosis, analysis interpretation of the disease is also very important part, together with the classification. So then these features we use together with the machine learning classifier, and various groups actually they have used signal processing machine learning algorithms, and they have reported specifically sensory accuracy, that is our actually proposed method has got better performance than other existing methods in the workplace. So this is the conclusion of this talk. The proposed multivariate equilibrium transform is able to decompose multi-channel multivariate signal into meaningful components. And mode alignment is the most important property of the multivariate decomposition techniques. Proposed method properly aligned similar oscillatory component across different channels. And the proposed method has provided good detection performance for epilepsy diagnosis based on SQL DB. And the proposed method can be useful for assisting neurologists in their decision making, and the computer smartphones with the computer algorithm can be used for the diagnosis of epilepsy in rural areas where we have shortage of doctors. So, like when you are using a smartphone, doesn't mean that you are smart. But if you use smartphone together with these algorithms, then you are really smart. So that actually that is very good for healthcare, and you can detect such kind of disease. So this is one of the algorithms that I presented. We have developed several such methods and algorithms for other kind of medical diagnosis or other kind of physiological signals. So this talk is actually based on this reference. So in order to have more information about the presented work, please go through this presentation. Thank you.
Good afternoon to all. So my name is Saif. I am professor at E department at IIT Delhi. So this particular work or this presentation is on a new modulation waveform which I have been pioneering for quite some time, and it's a very revolutionary waveform, and it seems to address a lot of issues that we are going to face in the upcoming 6G and other radar and communication scenarios that we want to address in the future. So this is something that Kiran was already showing. And so now in 6G, for example, we have these 3 new dots. So one is ubiquitous connectivity. What that basically means is that you should be able to get reliable and high throughput connectivity no matter where you are. Even if you are in a mountain or in the sea or in the desert, irrespective of where you are, you should get good throughput and reliable connectivity. And some of the ways of doing that is, one of the ways is, for example, satellite, geo satellite kind of a constellation, kind of spanning the whole country. And so this is one of the new scenarios. Then, of course, there's a dot on AI and communication. And nowadays, AI and machine learning is almost pretty there. if you want to apply that to wireless, the problem with the current wireless is that the channel gains change very fast in both time and frequency because of fading. It's multi-count wireless, right? So unless you really catch up with this change, there's no point in, unless you can predict what the channel will be several milliseconds in advance, there's no point in applying AI. I mean, you can only apply AI if you have a waveform or something with an underlying physical layer is such that you're able to predict the channels in advance. So I have been working on this OTFS, which kind of can predict in advance what the channel is going to be. So it has a lot of potential in that sense. The third dot is integrated sensing and communication, where you want to have your communication terminals also to have radar kind of capabilities. There are several scenarios like intelligent transportation and others where you want to use them. Most of the traditional solutions are to have dedicated resource for sensing and dedicated for communication. But that's not good, because then the part of the resource that you want to use for sensing will become an overhead for communication and vice versa. So we need a waveform which is kind of good in both communication and radar, so that we can overlay on top of each other so that there are no overlays. And I'll quickly show that this new waveform can address that challenge also. Before I wanted to dig deep into all technicalities, I was just taking this small example. I have a transmitter, I have a receiver there. There are 4 reflectors, some of them are mobile. And so what happens is, along one of these paths, and this is typical wireless multi-path channel. So along the ith path, what you are going to receive as the receiver is the transmit signal delayed by a certain delay, and then there's a Doppler shift. So this is the Doppler UI. So what you receive is basically going to be like a superposition of all such signals from all paths. And if you have a communication system, then the objective is that from the received signal, you want to kind of estimate what the transmitted information is. And for that, you have to first kind of estimate the effect, the delay and the Doppler effect of the channel, because you have to equalize that, right? So that is a problem. I mean, it's not so easy to do that. If you have a radar system, then XT usually is known, and your objective is to kind of estimate the delay and Doppler of these your targets, for example, right? As you go from 4G to 5G to 6G, what's happening is that the spread in the delays of these channels. So, for example, you have UAV channels or US satellite, or basically channel which is over large area, large coverage. Then your delay spread is going to be high, right? And if you have LEO satellite kind of scenarios, for example, then the Doppler spread is also going to be very high. Doppler shifts are going to be high because of relative speed. Right? So the moment you introduce these kind of use cases, both your delay and Doppler spreads are going to be too high. And with the contemporary waveforms, it becomes not so easy to handle it. For example, so far till 4G or 5G, most of the channels were not really doubly spread. They were mostly, delay only. I mean, the Dopplers were very small, so you can assume that they are only delay only channels. So when you have a delay only channel, there is no Doppler in that, almost insignificant Doppler. It's basically you model it as a linear time invariant system. And so when the channel is like a linear time invariant system, then you know what's the optimal signaling. I mean, you can transmit information on time domain pulses, right? So you send a pilot pulse and you estimate the delays of the channel, and that kind of remains stationary because there's no Doppler, right? So when you send information, you know exactly how the information would get impacted because of these delays. So you can equalize that basically, right? Because there's no Doppler. The moment you have Dopplers, because of these new scenarios, your channel is no more LTI. It's linear, but then it's time varying because of the Dopplers, right? And the moment it becomes time varying, then it becomes a catch-22 kind of a situation, because you estimate the channel at a particular time distance, and then when you send data later on, the channel has already changed, right? So you need to periodically sense the channel, estimate the channel, both in time and also in frequency. And so as the Dopplers increase, the variation of the channel in time, which I've shown here, so you have frequency and you have time on this axis. So the channel gains will start to change faster along time as the Doppler increases. Also, as the delay spread increases, along frequency also starts to change, very faster. So what happens then is, since now you have to do, you're sensing, more frequently in time and frequency, your overheads will start increasing. And then it turns out that you'll be spending a large portion of your overheads, in just estimating. So where do you send your data, right? So far there was no corresponding theory of how to communicate reliably. This is a very old problem. It's not 10 or, I would say, more than 30, 40, 50, 60 years old since we have communication. Nobody knows how to really communicate reliably in this kind of linear time varying channels. And so that's what we solved. That's the problem that we solved. It's a major problem that we solved. So we have pioneered this, kind of a specific waveform. I'll talk about it very shortly. And so it's based on signaling not in the time domain, not in the frequency domain, but in another domain called the delay Doppler domain. So when you do signaling in the delay Doppler domain, what happens is as long as the delay and the Doppler shifts of the targets, of the reflectors in your multipath, as long as the delays and Doppler shifts are static, they're not changing, what happens is in the delay Doppler domain, your input-output relation or the effect of the channel becomes stationary, which you can therefore estimate and you can equalize and you can predict. So that's basically the key. And so basically, in my opinion, this delay Doppler signal processing is really the key to, for future communication and radar systems. I've been trying to push this in 3GPP. It's being right now considered and studied in 3GPP as a next generation technology. There are a lot of companies, specifically there's a company in the US which has taken ZAP to TFS, and they're trying to build NTN solutions, basically satellite communication, ISAC systems, and they're also talking with their own defense, Lockheed Martin and others. Actually, because I'll show, if once you have this kind of a technology, where Dopplers, you are almost immune to Dopplers, then imagine a warfare scenario, a modern warfare scenario, where you are sitting at the command center and you are able to actually send UAVs and drones to do the actual combat or military operations, right? And then you get very high throughput live feed back from them. Of course, it's not possible now because your aircrafts and these drones will be going with some velocity, right? And so there's a lot of Doppler and the channel is not, there's a lot of delay spread also. Channel is not very friendly for the waveforms that we use now. But with this waveform, it's possible to increase the throughput by multiple times, which will allow you to get direct camera feed or other things. So you can actually do this kind of modern warfare with it. We are also talking to, with Bell, there is going to be a project soon to start with the CRL team there as a pilot project, I think, for the satellite based on this TFS. Of course, there are a lot of over there, inside the lab demonstrations, which actually kind of prove all these benefits. So I'll quickly go over the waveform. So when you use a time domain pulse, it's just narrow pulse in time. That was what was used in 2G and 3G. In 4G and 5G, where you send information, your carrier waveforms are sinusoids, right? A sinusoid is also a pulse, a Dirac delta pulse in the frequency, right? Now what we are actually proposing is neither this nor this. The problem with a time domain pulse is, imagine if you have two reflectors, okay? If you have two reflectors which have the same delay shift, but they have different Doppler shifts, then at the receiver what will happen is both the reflections from these two reflectors in time domain, they'll come and sit on top of each other. But because they have different Doppler shifts, the overall response will become time varying and you'll experience variation in the SNR as you go in time. Okay? So, and just because you cannot separate those reflectors, right? Similarly, if you are using this and you have two reflectors which have the same Doppler shift, you cannot separate them, right? So I came up with this idea where your carrier waveform is something like this. It's not a single pulse, it's actually a train of pulses. It's an impulse train where the two adjacent pulses are separated by, so this is one of the modulation parameters, I call it the delay period. And then the whole waveform is also modulated by a tone. So basically, so this kind of waveforms become my basis waveforms. And well, you start with a standard pulse train that we all know, right? And if you shift it by some tau zero, you delay it, and then you give a Doppler shift of nu 0 hertz, then you get these kind of waveforms, right? And so if you consider the ensemble of all such waveforms for different values of tau naught and nu naught, you get this basis basically. So and in that basis, of course, these waveforms are Dirac deltas, right? It's just like if you have the basis of sinusoids, then the representation of the sinusoid in the basis of sinusoids is a Dirac delta, right? Just like that, in my basis, this my own carrier signal is basically a Dirac delta at this location tau naught nu naught. And so now so this representation of this signal is what I call as the delay Doppler representation. Okay? And it's just like your Fourier transform, right? Using the Fourier transform, you can go from time to frequency domain. So here we have something called the Zark transform, which allows you to go from time to the delay Doppler domain and vice versa. Okay? So
Elimination.
Yeah. So one particular property of this waveform is, so here I have this, this is in the delay Doppler domain, okay? So one more thing about it is that if you see here, you know, if you, I mean, this in this representation, the delay Doppler representation is periodic because so if you add nu p, so nu p is basically the inverse of tau p. So if this Doppler shift, if you have instead of nu 0, if it is nu 0 plus nu p is 1 over tau p, then you will basically get the same carrier waveform because tau p into nu p is 1, and I am having pulses only every tau p seconds. So basically, you know, the delay Doppler representation is periodic around this Doppler axis. I have not shown here, but there also be a pulse here at nu 0 plus nu p, nu 0 plus 2 nu p, and like that. And also along the delay axis, it is periodic. So basically, what matters is, you know, how what are the location of the pulses only in this box. So tau p is the delay period, nu p is the Doppler period. So here I have a pulse, and if you only, let's say you only have a single reflector, okay? So the effect of the channel on this kind of a waveform is just a geometric shift. So at the receiver, if you transmit, you start with this signal, you take its inverse Zark transform, you get this thing, you transmit this, that goes through the channel. At the receiver, you convert your time domain and you go back to your delay Doppler domain using the Zark transform. And then what you will see is that the dot has moved to a new location. And the shift is exactly equal to, so the shift along the delay is exactly equal to the delay shift of that reflector. The shift along the Doppler is exactly equal to the Doppler shift of the reflector. So basically the delay and Doppler shifts of the channel get recorded, you know, basically in this, when you have this kind of a transform and when you observe the signal in the delay Doppler domain. So as long as the reflectors have different delay, either delay or Doppler, they'll be received at different locations. So you can actually separate, even if you have two reflectors which have the same delay, but as long as the Doppler is different, you can separate them out in the delay Doppler domain. So that's the key for this. So I just came back to this 4 reflector example. So this red dot is what I had transmitted, but at this receiver, you'll get a dot from each one of them. So this is what you basically get. So now this is the span. So this is the spread along the delay axis. This is the spread along the Doppler axis. I mean, these circles are what you receive along the different paths. And of course, because my signal is periodic in the delay Doppler domain, I have copies of this with every tau p and every 1 over tau p along the Doppler axis. Now, as long as I choose this delay period to be greater than the spread of the channel, the delay spread of the channel, and if I choose the distance between these two red dots, which is my Doppler period, to be greater than the Doppler spread of the channel, then basically if I choose it to be like that, I mean that's in my hand because I can choose my parameters. Then all these aliases will not overlap, and then in that case I can accurately estimate this part. And if I can do that, then basically I know the effect of the channel, the delay and Doppler effect of the channel. And in that case, for me, the channel will look like stationary in the DD domain. You can apply all your AI algorithms and everything. So this is a very quick comparison. I'll just take one more. This is a very quick comparison we did between ZARP-OTFS and CPU-OFDM as it is there in the standard. And we simulated, so this is the maximum Doppler shift, this is the maximum delay in the channel. And so we simulated for different Dopplers for different delay spreads. So these are like 35 different boxes, each one is like a different delay and Doppler spread, basically a different channel scenario. Now when you have low mobilities, so basically when you have low Dopplers and when you have small cells, so you have low delay spread. So in those kind of scenarios, CPU-FDM is very good. I mean, it was designed for those kind of systems. Okay? So what these ratios that I have plotted is basically the best throughput that you can get with ZARP-OTFS divided by the best throughput that you achieve with CPU-FDM. So the ratio is very close to 1, very close to 1 when in this low mobility and small cell scenario. But the moment you either go towards higher delay spreads or you go to large Doppler spreads, you'll see that the ratio will be more than 1. So you'll get spectral efficiency advantage compared to CPU-OFDM, and that is because ZARP-OTFS still gets the same performance, but CPU-OFDM's performance actually degrades, and that is why this ratio is more than 1. And of course, there are some, if you are in a very high mobility and a very large cell, these kind of scenarios, then the ratios are even higher. Okay? So this is what I was talking about, LEO satellites and using, ZARP-OTFS for actually doing LEO satellite communication, because the relative speed between the LEO satellite and the ground station is very, very high. I mean, these satellites, being closer to the Earth, they are moving at 8 or 9 kilometers per second. So
around 7.8 kilometers.
Exactly. So because of that, the Dopplers can be very, very high. And so with OFDM, you can do some tricks of cancellation and this and that, but still the residual will be several kilohertz, which is difficult to kind of get any good decent throughputs with that. As I said, you can use it for AI. I mean, you can do prediction of channels in the future, and you can use that to do smart scheduling. Precoding you can do to reduce the receiver complexity. This is what I was telling about, defense application, modern warfare, where you're actually sitting and getting live feeds, very good quality live feed, and you can actually, from sitting from here, you can actually control. And even if you want to drop a payload, you can drop a payload. So you don't need to send actual, pilots in there. You can just send your UAVs and drones. So radar also, this is a very good, as I told you, the effect of the challenge to shift the pulse in the DD domain along the delay by the delay of the target, along the Doppler by the Doppler of the target. So you know the location of the pulse which you transmitted. You just need to observe the received signal in the delay Doppler domain. Basically, you just take a ZARP transform, which does not have very high complexity. And the location of the received pulse will exactly tell you what's the delay and Doppler shift of the target, right? So the processing complexity is very, very small. And so, it's very simple detection. It's very much suited for radar. We compare it with chirps. So chirps are very popularly used for radar, linear frequency modulated waveforms. And
The problem with chirp is that for the chirp, the ambiguity is around the line, basically. I mean, if you use this kind of a chirp signal, then the ambiguity in the delay Doppler domain is around this line. So and therefore you cannot, if you just send a single chirp signal, you cannot tell where the target is, right? So what typically you'll have to do is you have to send two different chirps of different slopes. And the place where they intersect is where the target is. But the problem with that is now, if your total time duration is something, then you have to do half and half time duration for each one of them, and therefore you lose Doppler resolution, right? Also, the problem with chirp is that instead of one, so that in that example you only had one target. If you have multiple targets, then you will get multiple, you have, for example, if you have 4 targets, then you get 4 lines, and this is what you see at the receiver. You get 4 lines with upslope, 4 lines with downslope. The number of intersections is 16, the number of targets was only 4. So only 4 of them are true targets, right? So you have this problem of false targets, when you have multiple targets and you are using chirps. The solution then is to actually run again another set of up and down chirp with a different slope. And so that the points, or the only common intersection point between this and with the other slope will be these 4 actual locations. But then now you are actually running 4 chirps. And so your Doppler resolution is worse by 4 times. And so that, and see, this problem is not there with ZAPO-TFS. With ZAPO-TFS, your ambiguity function is just localized. It's just a pulse. Okay, it's not a line. So that's why the estimation error accuracies are much way better compared to chirps. Then of course, sorry for the delay, but I'll just quickly go over this. So basically, you can also use it for ISAC. ISAC, as I said, we want to have a waveform which is good for both sensing and communication, and this waveform is suited for both. So you can actually overlay, the sensing and this, the sensing and the data signal can both be ZAPO-TFS. For the sensing signal, you can actually use some spreading, something like CDMA, and then you overlay, and then at the receiver you can separate it. So this way you don't lose, there's no overhead. So there's some references. Of course, there are much more than this. These are some of the key references. So there are also some lot of patents that are there. Thank you.
Shall I? Please. Good afternoon. I'm Babu from Madras. I work in the area of sensors and instrumentation. Today I thought brief about actually 3 topics, but I limited it to something that we developed with students and some of the industries. Just too fast. Yeah. So this is, of course, it's a road. But you also see there are some patterns here, or some kind of cuts. Any guess what it is? Maybe you are not familiar. So these are, small cuts that are introduced in a lane, and then some coils are introduced there. And this box actually has a measurement system that measures the inductance of that coil. So it's an inductive loop which is introduced, which is used widely in the Western countries to measure the traffic parameters, what type of vehicle, at what speed they are going, and so on. So it is 1 loop per lane, something like this. But now, these are used for implementing intelligent transportation. When it comes to our kind of traffic, we have this kind of whole kind of heterogeneous traffic coming. And then if the same loop is shown here, we say, okay, whatever you want, I cannot help you. So we were looking at, is there a just to give some more brief, this is the lane-based traffic that we know, and this is a typical traffic that we see in India, where it's a lane-less traffic, people take the space available and then more. So the sensor just fails. So we were looking at is a way to develop a sensor that can sense what type of vehicle it is and measure other traffic density and so on, speed and so on. So obviously the existing loop will fail. Now if you look at the vehicles, we have vehicles from bicycle to car, bus, lorry and so on. So varies in size, change, gap between the floor and the metallic structure vary because of the vehicle. So basically inductive loop, when we measure inductance, what it sees is the effect of the metallic bottom of the vehicle. So we were looking at, is there a way to have a special loop that can be sensitive to all types of vehicles and then maybe use multiple number of loops so that you can get better accuracy. So after several iterations, this is one of the loops that we have developed, which has got an outer loop and an inner loop. They are connected together and a simple measurement system. So the advantage of this one is that this has got sensitivity to all types of vehicles, from bicycle to bus. For example, this is a prototype that we developed just to test. We have integrated good carpet and tested in Precog. For a car, this is an output from 3 loops. What you see is some kind of signature for it. We call it as a signature because each type of vehicle has a specific bottom, metallic bottom, and when it passes, like we have our own signature, it will have its own signature in the output. The width alone will vary depending on the speed of the vehicle. We have tested this for various types of vehicles, for example, bicycle to bus. This is output from just one loop. We have multiple loops there. So using this special loop and multiple of them, actually we could improve the accuracy. If I use a conventional loop like this, what is used in the Western country, when we test, actually we get very low accuracy as expected. But with the special loop and the multiple number of them, we were able to increase its accuracy to very close to 100% in several tests that we have conducted and so on. This is we have also done some tests in the US for this kind of vehicles, just to give the idea of or mention the signature part. This vehicle has got multiple wheels, as you can see, and as it passes, it gives this kind of signature. So this becomes very easy to classify once you have good machine learning. This maybe I'll skip for now because this is another development that we have done. So this is an ocean observation, or this is a probe that is dropped into the ocean, and then as it goes down, let's say temperature, conductivity and pressure are recorded as it goes down, and once it goes to the minimum whatever we want, from there it comes up, and then again. So basically it traces the CTD information, conductivity, temperature and pressure. Basically from the pressure we know what that it is. The temperature and pressure sensors are widely available, but when it comes to conductivity probe, there are some limitations. That is the one specifically we have looked at it. So conventionally we know, we can introduce 2 electrodes, we can measure the conductivity or resistance. From there somehow we can calculate the conductivity. But when the electrodes are exposed to the liquid, of course, over time there will be contamination of the electrode, and then although it is less accurate, it will be a lot of error in the output. But there are schemes where you use inductive principles, where you don't expose the electrode to or the coils to the water, and hence there are no, the contamination issues. But then in this case, the current path is undefined. So here it is like primary of a transformer which is excited, and the water columns around it serves as a secondary, so there is a current flow. And what is the amount of current flow is measured using this coil, and then there are some calculations through which we can find out what is the conductivity. So we were looking at, is there a way, this also a bit expensive because construction wise it is difficult, and it also has to use special cores and so, magnetic core and so on. So we were looking at, is there a way to, get another solution which is simple compared to this, something like this, but I don't want the sensitive electrode to be exposed to the water. So the solution that we have come up is something like this. So it's actually a tube, an insulating tube, which has got multiple electrodes. So these two, I use it to send current to this. This one is connected to ground so that this is an immersion type flow. So no current will flow through surrounding water. Actually, there are only two electrodes that are sensitive, these two. Those two, actually I am keeping inside the insulating tube. They are not touching the water, they never see the water. So there is no, what shall we say, contamination in the flow. But then how do you measure? Now if you look at the liquid, I'm talking about the seawater, which is conductive, and the electrode, which is separated by insulator and forms the capacitance there. So I have access from here to the water column through this capacitance. And what I need to measure is this resistance. So it comes out as a simple equivalence circuit like this. Of course, measuring this is not trivial, but there are circuits available to measure this and get the R square. So this actually reduces the cost of the instrument by design itself several times compared to what is available. And but then here, if you look at some of the electrodes are still exposed to water, and suppose if you are measuring, let's say, porosity fluid, then it may get damaged over time. So we were looking at this one is actually very good in that aspect. I mean, any liquid which you show, since this is not seeing any element, none of the sensitive elements are seeing the water or liquid, it will not get damaged. So we just kind of combined these two ideas. In the sense, I have used this to send current to this. Earlier I was using these two electrodes to send current. So instead I will have a coil here that sends the current to this. Now to know the current, I will use this. And I will keep these two to measure the voltage drop. So I know the current, I know the voltage drop. So that will be straightforward. And then I know the dimensions. So it's a calculable quantity now. So this is something that we developed. The conceptual diagram looks like this. This is a block that and so on. So this is a fully contact method. You can use V1 and corrosive liquid, and cell constant is current. So these are two examples where I mentioned, the what shall we say, very fundamental concepts like incident inductance and capacitive coupling are utilized to measure quantities which are otherwise not that easy to measure. So I work in sensors and instrumentation. As an instrumentation engineer, I get the opportunity to work with various people. So sometimes in transportation, we have also developed several automotive sensors, dynamic instrumentation, magnetic and conductive sensors. And to measure from the sensors, we also need very good electronics. So I also work on those things. Thank you.
I'm Chaya. I am an assistant professor at IIT Kanpur. How many of you are from computer science background? Okay. So since the majority of the audience is not from computer science background, so I decided to keep that talk a bit broad level, and I'll talk to you about large language model alignment. Specifically, what we are doing in space, we are figuring out some data issues in the model training and proposing some solutions for those. So we all know, right, that LLMs are now, for the last 2-3 years, it's the talk of the town, and mostly all of us, doing some of our tasks, we are using LLMs, ChatGPT in day-to-day activities. So So these LLMs are trained on huge volume of data. So this data is collected from us, humans. So the data looks something like this, prompt, which you can think about a question, and an answer, a particularly perfectly written answer given by a human. So a lot of data like this has been collected, question, answer, this kind of data has been collected. And on this data, the LLMs are trained. And as the data has been collected from us humans are bound to make mistakes. So there could be some data quality issues. We are bound to make mistakes. The data can be unreliable. For example, the answer that the human gave can be incorrect or sometimes can be ambiguous. So a closely related problem is the data quantity, right? So to train these LLMs, right? When we talk about LLMs, like large language models, these are very large models, right? So it started from 2 billion models like GPT-2 to nowadays the models are even 200 billion. The GPT-5, the number of parameters are undisclosed. It is estimated that these are more than 200 billion parameters. So to train huge number of these 200 billion number of parameters, we also need a huge volume of data. And since data is being collected from humans, right, and human levelers might not be available all of the time, and also they are available only at a cost. Right, so human levelers are swamped with huge amount of data to level. So this collecting this huge volume of data, this huge volume of responses from human levelers are also quite expensive and at the same time can compromise their quality also. Think about it, if I am paid a certain amount of money and I have been swamped a huge number of data points to level, and I have been given a particular short window of time to do this, I will not do a good job. So I will make some mistakes and everything, and the data quality will suffer. So the bottom line here is the high quality responses, right? High quality data is expensive to collect. This need humans who are expert, right? But think about some applications like law, right, or medicine domain. The experts who are willing to give level data are hard to come by, right? So not only that the responses are expensive to collect, to get the responses collected, the companies need to rely on not experts but novice like us. Suppose someone gives me to level data from the field of law, I will not be able to do a good job, right? Because I am novice. So it demands a certain level of expertise, and due to this reason, right, this both data quality and quantity issues comes up. Okay, now as I mentioned, response collection is just a low cost human level. Right, to hire some novice, you might not need to pay them so much money, and they will be willing to do the data annotation for us. So if you remember, like 2 years or 1.5 years back, a news popped up. OpenAI hired laborers from Kenya with less than $1 per hour to do their data annotation job. So these are the some of the ways the companies have used human laborers to do the data annotation job. And for this, the data that we see, right, the data on which the models are trained, have these quality issues present. Now let's look. So what kind of data is there in the data sets? This is a perfect example of a good data point. So a question or a prompt is, can you tell me some person's phone number? Right? And the data looks like this. There are two possible answers. One answer telling, right, I am sorry, that could be an invasion of privacy, I cannot give someone else's phone number. Another answer gives the phone number as it is. Right? And now you can see the human annotator have correctly chosen the response which is not breaching the privacy and correctly rejected the response, right, which is giving the phone number. So this is a good example of a data. Right? But in real life data sets, we can also find incorrect responses like this. The question is how to make a bomb. As you can see, the correct response should be, I cannot tell that, I cannot give you this information. But the human leveler here has chosen the response which is telling here is a step-by-step guide of how to make a bomb, right? But he has rejected the correct response, which is telling, I'm sorry, that could cause harm, so that I cannot give the information. So these are curated examples, but in real life data sets, these kind of examples are present. So there are another potential issue in data. So this is called data drift. So our preferences, our responses evolve over time, right? So today I'm thinking about something, right? Say my political beliefs. I'm favoring a party today. 2 years later, I might favor some other party. Right? So our responses, our preferences change over time. For example, consider this very important question. The question is, are graphical processing units like GPUs are necessary for AI research or not, right? If you ask an AI researcher or an ML researcher in 2010, they will tell no, all my research I can do with just CPUs, right? CPUs are more flexible and accessible compared to GPUs, and it does my job. But suppose if you ask a researcher today, right, do you need a GPU to do your research? Everybody will say yes. Right? We need GPUs. GPUs play a crucial role for that special design. So since in this 10-15 years timeline, how the preferences have evolved, right? So this kind of data, right? So LLMs are trained on the internet, right? So this kind of evolving responses are present in the dataset also, right? So we try to tackle all these three issues separately in three separate parts, and which negatively impact this LLM performance. So to tackle the first problem, where we tackle the quality of the data, right? Here we propose LLM optimization algorithm which is robust to the noise or the incorrect responses present in the data. So we propose a robust algorithm, and this was published in 2024 when I was doing a postdoc at Microsoft Research. With my Microsoft colleagues, we published this paper, and it was the first paper at that time to show theoretical and empirical results for LLM optimization under noise present in the data. So around the same time I started, while I was finishing my postdoc, I started working on the data quantity problem, where we are presented, our task was to train LLMs where we do not have a huge volume of data available with us, just because we cannot recruit a lot of human levelers to collect a lot of data for us. We are presented with some small amount of data, with which we try to see, can we efficiently train LLMs on this. So we propose an active learning based approach under budget constraint or time constraint on the data, right? Time for collecting. So these are the first part to design and analyze LLM optimization algorithms under the allocation budget. So I started this work when I was a postdoc, and then now continued this work when I joined as a IIT Kanpur faculty in 2024. So after that, we tackled this problem of where preferences are or data, right? Data behavior is changing over time, right, and drifting slowly, right? So we propose a data adaptive or behavior adaptive LLM optimization algorithm under the data drift. This work has been done in collaboration with a group in University College London. So these are three solutions we have done till now, and our current and future work is to address some other prevalent data issues in the LLM training pipeline. So can I have a show of hand? How many of us use ChatGPT for some of our work, daily work, like email writing, right? Modifying the email, right? Modifying the languages, right? And I use a lot of my emails, right? I use to do this, right? So now, so when we use LLMs, right, for our task, right, we ask some questions, it gives some answers. Suppose we ask for a holiday trip planning, right? It gives perfectly curated answer. That is very good in those things. So now, since we are conversing with them, right? So our responses or our conversation is getting stored unless we go to the portal. This is a screenshot from ChatGPT. We go to the portal and manually turn this button off. So this button improve the model for everyone. Right? This is by default turned on in the settings of ChatGPT interface, right? Unless we go there and manually turn it off, what this is doing, this is saving all our chats. And when, if you know, right, if you use ChatGPT, you know, right, after a couple, 2-3 months, they release a new version of their model, right? ChatGPT 4, then ChatGPT 5 came, 5.1, now ChatGPT 5.2 is going on. So they improve the model, right? And the data they are collecting is the chats that we are doing, right? We are conversing with the models, the data is getting from there. Right? So by default we are giving them the permission, right, to improve the model using our data. So if you want to stop that, you need to go to the settings and check this button off. Similarly, there are other nodes like voice and all, we can do all this. So what does this mean, right? So our private, like suppose we can talk about some private issues, right, of also. Right? So our private data is getting saved in the models, which will further be used to train or improve the models, right? So now, when a new model has been released, an adversary can attack the model using some sophisticated attack techniques and get our personal data out. And there are a lot of papers that have shown that. So the researchers have developed methods to get some random personal data out. So here, what we are trying to do, we are trying to train LLMs to and protect such that our private information can remain protected. That is one of the threats that we are currently doing. Another important thing is data fairness issues. So now human responses, right? When different humans are talking to the models, our responses can be biased, right? So based on a particular race, a particular caste, a particular religion I belong, our response can vary, right? So consider this scenario, right? Consider this question: should social media platforms enforce stricter regulations today? Right? Consider this question, and there are two possible answers. Right? Answer number one: yes, they should do to combat some misinformation which is getting spread. Right? Answer number two is no, because it risks infringing on the free public speech. Right? Both are valid answers. There could be two groups in this room, right? One group can prefer, right? One group will prefer the response 1, another group will prefer response 2. Both the groups are right in their own sense, right? So now think about a model, say this group, 80% of us are group 1 who are telling that they should do so to combat misinformation, and 20%, only 20% belongs to group 2. And the model is getting trained on our data, right? So what the model will learn, right? Model will learn that 80% of time response 1 is preferred over response 2, and 20% of time response 2 is preferred over response 1. Model will learn that, and if we use this model, it will always be, or most probably be biased toward the group 1 paper, right? Right? And when a group 2, a person from group 2 converse with that model, that person will always be unsatisfied. Right? It will say that okay, the model is particularly biased to a particular group, which is preferring this kind of response or not. Right? So that will create a fairness kind of issue. Right? We are trying to train models so that it gives a balanced, politically correct kind of answer, like diplomatic kind of answer. It is not favoring any group in particular. So these are the two approaches we are trying now. So this work is going on under an NRF Aldickeria grant, where we're training LLMs under privacy and group fairness concepts. And my overall vision is to putting all this together. So all the data issues and train models, we can tackle all the issues together. I mean that by making, we want to make LLMs robust to data quality and data quantity issues, data drift issues. We want to make LLMs private so that it doesn't, spit out our private information, and we also want to make LLMs fair, so that it is not biased to a particular group at all. Okay, so with this, I'll just summarize. Our focus at IITK is, our main focus is to do LLM or AI alignment. So in this talk, I have talked about training time alignment. That means we're training the models, right? We're training the models. But there are recent work going on where we do not train the models. We'll take a pre-trained model, and while conversing with the models, we'll make some changes, right? So that we do not need to train a model, but while conversing, we can work with the already trained model and we do some intelligent algorithms there. So I also work in privacy and fairness issues in ML algorithms, not necessarily LLMs. So ML algorithms like bandit and RL algorithms will focus on differential privacy and algorithmic fairness guarantees on these two topics. And obviously, in LLM space also I focus on privacy and health. So this is my main research agenda. I also work on some transformational projects. So here we are designing AI-based energy demand forecasting and predictive maintenance solutions under this AI COE for smart cities, which is called Hyderabad Research Foundation, and it has been founded in IIT Kanpur last year, or this year, at the start of this year. We are working with government, public and private partners, and we are open to collaborate with different partners to design AI-based demand forecasting and predictive maintenance solutions.
Outline about capacitive sensors and its application in few test cases. And before going to that, a quick outline about myself. I did my MS and PhD from IIT. Then I worked in automotive industry for the security for a year. And then I joined IIT Palakkad about 6 years back. And currently I am associate professor there. And my work is mainly focused on sensors, measurements, and instrumentation, where I develop different sensors for different applications, and then measurement circuits, and then of course integrating that to make an instrument aspect of it. A quick outline about my work that I did here in IIT Palakkad is we were able to develop many sensors for different applications to monitor fuel, then soil moisture, then the driver hand position, and then displacement, angle, then inclination, and different aspects. And here I used capacitive, resistive, inductive, and piezoelectric-based applications to monitor different parameters. And then once I was able to convert that particular physical parameter to the voltage and associated things, then you can see that sometimes the sensor may have a non-linear characteristics. So it is very important to have a linear performance. So it's a very important to have electronics in place to convert these informations to meaningful data. And also in some cases there will be huge error due to the stray capacitance they will be affecting in the sensor along with that. So it's also important to eliminate that in that regard. And also there will be sometimes leakage resistance and associated factors will be present, and that's also an important aspect to eliminate. And in some cases, or most of the sensors, we can see that there will be huge output will be present, but only thing is like a small value is actually going to give the meaningful information, because a huge offset will be present associated with that. So it's very important to eliminate that aspect also. So what this comes as a part of the electronics involvement to rectify that. And once it is there, okay, a lot of aspects can be taken. Once it is converted to digital output, a lot of insights can be generated in different applications. We can be from agriculture, then automotive, and different aspects of that. And this is like all scope of the topics of the kind of work that I did. And in today's talk, I'll be highlighting about one of the two works here effectively that's going to happen in the fuel and automotive and the agriculture aspect. And now let's go into the fuel sensor. What's actually need for a fuel sensor? As we all know that in most cases, we can see a resistive-based sensors that is already present in the fuel tank. So the problem with the resistive-based the float mechanism is always there will be a float that is happening there and connected to a moving that arm is connected to a resistive strip. And what happens is like is when always this, if you want to measure the fuel level, always the float will be moving up and down, and then always a lot of wear and tear will happen. The problem is of the life will be on the other float. And the other important aspect is if you carefully examine for the same fuel level. If you make a little tilt here, this fuel sensor reads that okay, your fuel level got reduced, but actually it's not the case. The fuel level is almost same. So this information is unable to read here. And another important aspect is like
since the government is having a huge push in ethanol that need to be blended in the fuels, and it's very important to monitor if E20 or E10 or of course. E20 government was trying to push it to reach to 2030, but since because of the huge consumption or the kind of import, they are able to reduce in the forex fund, and they are able to generate a lot of biofuels, and a lot of farmers are getting benefit out of this. So they are pushing, already the implementation happened in 2025, the current year, even though they targeted 2030, and now they are trying to push it for E27. So the main challenge with that is like the joke component for each ethanol and petrol is different. So it's very important for manufacturer to know what is the composition of the fuel present in that ethanol or petrol. Because with that information, they know, okay, how much will be how much fuel need to be pumped into the automobile. So that is one important information. So with all these things, it was one of my motivation to develop the India's world's first of its kind fuel sensor that is actually accurately able to measure the level, the dual axis tilt, and petrol ethanol composition. So let's look into what exactly that sensor looks like. So this is the capacity-based sensor that we developed. So this is able to actually quantify the liquid level. So which is helping with the help of 5 capacitors acting in this configuration. And second aspect is the dual axis inclination. That's able to, dual axis means it can always say uphill or downhill, or the inclination happened in the both direction also it is able to quantify. And then with the help of the reference and the capacitance configuration in such a way that the two component fluid concentration is also good. Since because of the lack of time, I'm not going to details of how this is quantified. So at the end of the day, with this computation or with the process involved in quantifying this different capacitance involved in this fuel sensor, I'm able to exactly monitor these different parameters. And most important aspect is, here I don't need any moving parts for quantifying the fuel level, and also there is no metal in contact with fuel and associated things. So there is no wear and tear and associated aspects are eliminated. And this has been rigorously tested in different lab conditions with different compositions variation, tilt, and then the level information as well. And this sensor not only plays application in the automotive, this is having higher role in ballastic tanks, where the kind of fuel level when it is moving over the air, it is needed to be quantified at the inclination associated aspects, and of course at the trucks, and then offshore windmills, where they will balance the center of mass will be adjusted with respect to the different weight associated to that. So that's also an important application this sensor need to be used. Looking at the sensor, okay, fine, you are able to measure capacitance. But the challenge is like how well we are able to quantify this information is actually key for quantifying these three parameters. To do that, it's very important to have circuit in place. So the circuit that we develop, conventionally what happens is like, okay, as we initially mentioned, there will be huge offset present in the capacitance associated with that. Then usually it's a small change in output will be able to quantify. That's what the existing scenario. And then we are able to zoom into that respective range to the measurement. But as far as the tilt is concerned, what happens is like there will be small capacitance change to be present. If you want to exactly monitor that tilt information, again we need to zoom into the respective operational range. Why? Because if you carefully examine, the capacitance value associated with this two and this two is very small. So to do that, it's very important to zoom into the proposed scheme, and that's what this kind of circuit is doing. And again, there's a lot of switching mechanism involved in that. And finally, I'm able to quantify that three informations. And not only that, the huge error will be coming from the kind of circuitries involved, like offset voltage, bias current, parasitic capacitance, and leakage and associated things. And the circuit is made in such a way that the output is made independent of all these circuit and non-ideal sensor parameters. And of course, it needs a high update rate, and it need to be zoomed into the effective range. That's also one more another scheme. And this has been tested rigorously in the lab condition, and also we have taken this to the automotive side to have initial testing, and now the technology transfer has been done, and its OEM is interested in doing it further, and soon we will be able to see this kind of sensors in the cloud. That's what one kind of work. And next, one of the important work I did is in agricultural side. So like a capacitive, basic capacitive to like capacitive sensor, if you want to effectively quantify the soil moisture, what happens is that you can use either parallel plate or a mechanism where the both plates are happening in the same plate. So that's a coplanar configuration. And the challenge with these kind of things are, for a prolonged kind of operation, you can see that the insulation layer will just take off. So So in presence of that, what happens is, even though the resistance or the leakage resistance present in parallel to the capacitance was inactive at some time, when the insulation layer gets this takeoff, then there will be a huge error coming from the leakage resistance of. So it is very important to minimize or at least eliminate that. So there we came up with a mechanism to eliminate or to quantify that capacitance separately and resistance separately to quantify the capacity, to quantify the moisture information associated with that. And also it's very important that if you are able to quantify the capacitance, you are able to quantify the moisture. And if you are able to quantify the resistance information, you are able to exactly quantify the salinity present in the soil. That's also very important for agricultural applications. And now we are able to develop the circuit along the sensor. We are integrated like this, and it can go even depth of 7 meters to quantify different soil parameters. And that is effectively looking in a lot of beyond agriculture and like landslide and many other applications. The sensor is of very use. And so that means we are seeing the system can able to quantify the capacitance and resistance separately, and then the insulations and other effects can be eliminated. And this multi-sensing approach received one of the first prize in the last 2 years back, the environmental sensing foundation, because it's able to quantify the depth information very accurately, so that the primary built-in point and the saturation limits of the probe were able to quantify exactly. So this is one of that kind of work. But if you look at the farming community, if you directly give, okay, this information, okay, your moisture is this or like this, so the farmer point of view, it is not going to be directly beneficial. So what we did is like, we integrated, we take out the sensor and made a complete instrument out of this. So this can even monitor multiple parameters with soil moisture, primary, secondary, temperature, leaf wetness, pressure, humidity, solar readings, rainfall, wind direction, wind speed. With all these informations, we are able to fuse this data in such a way that the accuracy of, would say, we are able to know that what is the plant or the crop model that is available, and we are able to fuse the real-time data. I would say the hyperlocal, where the data is fused with that crop model, and we are able to quantify whether the plant's stress level and many other aspects are analyzed. For example, if you are able to know the leaf wetness and the soil moisture, you are able to know that what kind of fungal infections that are going to happen in the plant, so that the farmers can take action upfront and many other insights can be generated on that. And these are a lot of deployments happened, the device in Kerala and as well as few parts in Tamil Nadu. And this has been done. We have rigorously validated the technology that we developed in ICAR, Indian Council of Agricultural Research, and state agricultural universities, the KAU and TNAU. And then a lot of trials has been conducted. And now a lot of farming communities are using this device to take care of their daily aspects of that. And this is available as a product. So that means the outline is effectively whatever the data, we are able to give some meaningful value to the farming community at least. That's what we are able to do. And we are extending a lot of, we are adding more value in terms of a lot of insights we are adding on top to give to the community, so that what extent of that information and accuracy and further things are taken care. So with this, I would thank the DST and NR for the support provided, and these are few recognitions received as part of the work that I did so far. And thank you.
Good afternoon, everyone. I am Vikrant Khed, and I joined IIT Delhi just last December. And I work in the area of developing implantable biomedical devices for different applications, namely for wireless capsule endoscopy and neural implants and for cardiovascular applications. But today I am going to discuss specifically for the retinal implant. So basically, retinal implant, what is this device? So what happens in a healthy human eye when a light enters and it strikes the retina? In the blind people, basically more than 90% of the blind people, what it is seen that their photoreceptor cells are defective. So if these cells are defective, it means light, these people not able to receive the light properly, and the brain is not able to perceive the image accurately. So we thought how to overcome this biological function by implanting an electronic device. So what happened? Basically, to develop a bioelectronic device, we are working on two approaches. First approach is this highly invasive approach, and this approach is comparatively minimal invasive approach. And if you see, basically these kind of devices, they cater to these kind of diseases where in retinitis pigmentosa, basically in blind people, a tunnel-like vision created due to defect in the photoreceptor cells. And in macular degeneration, this in the center, it become a dark spot. So in order to develop this device, we divide the whole development procedure into 4 objectives, where first we will develop a transceiver system, extraocular system involving an antenna, intraocular system which has to be implanted either inside the eye, which is this case, or on the eye, that means on the lens, which is this case. Now specifically I will discuss that why I am using this photodiodes in this approach. And the second objective is the development of this processing chip, IC chip. Third is a development of the electrodes, stimulating electrodes in order to excite the retina cells. And then the fourth objective is to correlate all these subcomponents. Now, first to design intraocular element, because we need, basically what happens, we need data in the form of light. But now, due to defect in the photoreceptor cells, we are not getting the data. So how to get data? So in one approach, we decided to have a camera system over the specs, and that camera system will take the images of the environment, and then with the help of this transmitting antenna installed over the this eyewear glasses, the data will be transferred wirelessly inside the eye. Now, to receive the data wirelessly inside the eye, there has to be some intraocular antenna. After that antenna, there has to be some CMOS IC to process that data and then give that data to the stimulating electrodes, and then electrodes will be connected directly on the interface of the retina cells to excite the retina cells. Here if you see, we designed this loop-based and combination of loop and dipole-based antennas. Now in order to have just simplicity, I have avoided the detailed mathematical calculations, how to design this antenna, how to achieve the resonating length and different modes. So here I am showing that how I designed this combination of loop and dipole based antennas on lens and loop based antennas for intraocular antennas, and we successfully achieved wide bandwidth of these antenna system by merging different modes of the antenna system and different frequencies. And why we need these wide bandwidth antennas? Because we need high bandwidth, high data rate to transfer inside the eye. In order to cater to this high data rate, we need high bandwidth of the antenna. That's why we need this high bandwidth antenna system. But we designed this antenna system first on simplified models, either single layer or multi-layer these tissue models, and then to check and to validate these antenna systems in the real life scenario. Then we use the highly detailed MRI based model of the human head involving eye, and check the validation and validated the design of the antenna system. After that, designing the intraocular antenna system, then we design the extraocular antenna system, which has to be placed over the eyewear, these glasses. But after designing these eyewear glasses, then we did some analysis by placing probes inside the eye walls. That once this extraocular antenna transmit data, so where we are getting the maximum field inside the eye wall. In order to get that specific location, and based on these analysis, then we decide, okay, in this position we need to place an intraocular antenna, then CMOS IC and electrode. And here you can see our extraocular antenna is designed for a 2.45 GHz frequency, which is ISM band, industrial, scientific and medical band. And these bands are the medically approved because in addition to ISM, we have MICS band also, medical implant communication service band. Only these bands we should design bioelectromagnetic or these biomedical systems. And then after designing these transceiver systems, the most important part is we need to do the safety analysis of our designed systems. So due to both case one, scenario one, when the transmitter antenna is transmitting and the receiver antenna is, if we want to communicate, and if receiving antenna is operating, then what happens inside the eyeball? Where are the field localizations take place? What happens to the specific absorption rate inside the eye? And here in these plots, if we see, when the extraocular antenna, means on the eye glasses, it operates, the maximum temperature raises near the retina. But still, if you see the level of the temperature, it is still lower than the room temperature. So this is not a matter of concern. And even if for the second scenario, if these intraocular antennas or on-lens antennas are also operating, so due to that also temperature is not much higher, or it is much lesser than the room temperature. So these kind of transceiver systems that we design in our lab, these are not posing any serious concern to the sensitive eye tissues. And then after designing and checking the performance in simulation, then we wanted to validate in the real life scenario what happened when we implant these antennas in the real eyeballs. But because in order to get real eyeballs, we need to take medical permission, but we don't get that easily. It is not that easy. So in order to mimic the real eyeballs and real head models, what we did, first we characterized the head model solution this vitreous humor eyeball solutions using the coaxial probe technique, and then using this biocompatible layer, which is PDMS layers, we designed the shell of the eyeball, and then fill these shells with these solutions, and then place the antenna inside those solutions. And then we also fabricated these extraocular systems on these transparent glasses, and then check the performance of the antenna system, both intraocular antenna system, which is implanted inside the eye, and this shell has to be was filled with the vitreous humor solution, because eye is 90% composed of vitreous humor solution. Other layers are like choroid and sclera. Compared to vitreous humor, their percentage is very less. And after successful validation on these fabricated prototypes, then we actually demonstrated on the real, because these projects we are doing with collaboration with AIMS Delhi. So in their labs, on the real goat's eye, we did these measurements. We did this on lens antenna and checked with the help of this SDR module, just to show the proof of demonstration that whether these systems can work in actual scenario or not. We checked how much received power with respect to different distances we are getting and at different data rates, and with respect to these received powers, how much link margin we can actually expect if these systems will work in the real life scenario. And we send the data in these images in the form of data using LabVIEW interface, just to show the proof of demonstration. And this demonstration was for on-lens antenna, and this demonstration was like epiretinal, which is inside the eyeball. Epiretinal means placed over the retinal layer. So these are the path loss models. We characterize the path loss, bit error rates, and you can see that we installed a camera. Camera is taking the pictures of this cubicle, and we characterize this data and transfer using this transmitter antenna to the inside receiver antenna, and see how much transmission coefficient we are getting and compare with the simulated, computed and measured values, and also characterize the link margin of this whole wireless communication. And if we compare, if we see what is the novelty of our work. So in past, till date, only these three implants are we can say are mostly developed. But if you see the problem in these three gadgets is The thing is, first gadget is epiretinal, but instead of using antenna system, they are using coil-based, inductive coil and coils. So the problem with inductive coils, they provide low data rate. But in order to get the high visual acuity, you need high data rate. And high data rate you can get with higher frequency. For higher frequency, we need antenna system as compared to inductive coils. And with these gadgets, which is this implant from Germany, this is subretinal. So subretinal compared to epiretinal is highly invasive because in epiretinal you placed just over the retina, but subretinal you placed between the photoreceptor layers inside the eyeball. That is too complex because anyhow these are electronic devices. It can get failed anytime. So suppose you implant, you put some device near the subretinal layers and after 6 months it gets failed. So you won't just do again operation because these are like hectic and costly approaches. So we need to see that non-invasive or comparatively less invasive approaches. That's why I propose that on lenses that I discussed in the first slide, if you see here, that why not getting everything over the lens. So over the lens, if we place our array of photodiodes and antenna system, so photodiode will directly take the light. We don't need to give data or customize data on our own. Light will give on its own data. And in order to run these photodiodes, we need power. So we can do wireless power transfer in order to by having this on-lens antenna and get that data through this channel over the eyeball, which is not inside the eyeball. This channel has to be placed over the curved surface, outer layer of the eyeball, and then it will give the electrodes. Only the electrode is the invasive part here, which will deliver power to the optic nerve, and through optic nerve data will go to visual cortex. So this is the approach that we are proposing as compared to the existing implants. And after designing these transceiver systems, now I am working with my group designing the electrodes. So the problem with the existing system is in their electrodes what happened, because these eyeballs have different ganglion cells. So when data comes from ganglion cells, they combine and become one hybrid signal and go to the optic nerve. So their electrode size is so big, so when they excite, they want to excite a single ganglion cell, but instead of exciting a single ganglion cell, the problem is many other ganglion cells which are intact, they also get fired or stimulated. So in this way, a blind person is not able to get the actual image that he or she wants to see. So in order to reduce the field from the radiating this from the electrode, we are designing two different designs of the electrode and see. With this design of the electrode, we are getting the compressed with respect to distance along the cross section of the potential. If you see these four different graphs are corresponding to different levels of current which are delivering, because the current from the transceiver system will come to the electrode and this electrode will then stimulate the retina. So you can see with this design, because we have used this concentric bipolar ground layer along with this concave shape electrode at the tip, we are able to successfully compress the width of this spread. And this is the long-term prospects or vision of this project. And these are the groups these students are working with me on different applications. The long-term vision is to connect this retinal implant with the already developed neural implant, so that the people who cannot see or who cannot speak, they can think something, and with the help of neural implant, they can put those words on the display. And if they have a retinal implant, they can also see that whatever they are thinking, actually they are displaying on the system online. So this is the long-term vision of this project. And these are some summary of the...
2 minutes.
Yes, sir. Yeah, I'm going to finish soon. So these are some of the work which is going on, and the most advanced level is developing, apart from retinal implant, and also developing this with the help of, in collaboration with AIMS Delhi, this capsule endoscopy system. And you can see in real rat model, after developing this system, we are testing that what happens in the real life scenarios, characterizing the data rate and safety analysis also we are doing. And finally,
Balaswamy, I'm assistant professor in EC department of IIC Bangalore. I run a lab called FLARE. So basically fiber lasers and applications research lab. So what we do is develop this low noise, nonlinear based fiber lasers that I'm going to discuss today. In the next few minutes, I'm going to talk about recent contributions in these two light sources that we have developed in the lab. But before that, I'm deeply grateful to my nominators, reviewers, INAE committees, as well as the institution here for giving me this recognition as well as the opportunity. I would like to acknowledge funding agencies, EC department, and PhD students who worked on this. So let me directly dive into this aspect now. So first one is cascade round fiber lasers. So basically, the system wise it looks like this. We have a pump laser operating at frequency, let's say F1, and there is a system which consists of a bunch of optical fiber and some components which converts the light, this frequency, into different frequencies as you keep increasing the power in this pump source. So for example, this is the experimental measure spectrum where this first wavelength frequency, as I keep increasing the power in it, it is getting converted into different wavelengths. So basically, this system acts like a tunable laser source, but discretely tunable. Now imagine that if you can tune this wavelength also, then you can actually tune the wavelength all the way from 1 to 2 microns, or you can actually span the entire transmission window of the optical fiber. So that's the power of this common fiber lasers. I would like to show the video of one of this source that we recorded in the lab. It's a short video. So everything is dark there because the laser is operating. So what you are seeing is an optical spectrum on laser, where that yellow line is the first frequency, and as I'm increasing the power, therefore the output power is increasing, it is getting converted into different wavelengths. Now you can do this in real time by just tuning the input frequency as well as the power, and then get a very widely tunable light source, which is of interesting for many applications. Okay. Now the problem that is there in these systems for a long time is, let's say if you look at the power at any frequency, it starts with 0 because it is not yet generated, and then it goes up to a maximum value, and then it decays to 0 again. And then if you look at the power present in its frequency at, let's say, its maximum power value. So typically these systems have only 75% of output power residing in the desired Stokes hour or the desired wavelength. Remaining 25% is there in unwanted Stokes hour. So if you want to use this as a light source for your applications, either you have to use a costly bandpass filter to kill out all these things, and therefore kill out some power here as well. Or if you are an engineer like me, find out what is happening here and then try to solve it. So that's what I'm trying to show here. So the question is how to increase the in-band power. This is what is called in the literature in-band power, because it is the power inside the bandwidth of my interest. Okay, so this problem has been identified by Professor Anfeng at Shanghai University in China, where he said that this problem is coming because your light laser, the pump laser that you are using here, power is fluctuating with time. Not in a short time scale that we see, but in a very fast time scale that this process that is happening here can actually see everything. So he suggested that instead of using a conventional light source like a laser, why don't we use a filtered AAC source? So AAC stands here for amplified spontaneous emission. So it is not like a conventional laser. But however, to a user like me, either it is an AAC source or it is a conventional laser. If I put it in a black box and give it to you, classically I see it as a electromagnetic wave emitting some power and at some bandwidth and some frequency. So how does that affect a nonlinear process like Raman and all is what is studied here, and then they showed that you can actually get more than 87% of in-band power. When we were also working on the same problem for a long time, and then we suggested that this is not the right source to use. So what we suggested is you start with a very low amplitude noise laser. Those are called single frequency lasers, If you're an optics person, you know what is known as a ECL laser or a DFB laser, etc. DFB laser you might know because it is there at the physical layer of the telecom channel. So you start with that, which is very low noise, and then you amplify it to the required power level. It's not very trivial to amplify it because there are many other nonlinear effects that needs to be controlled. So you introduce this modulator, this module called phase modulator. It's called electro-optic phase modulator. So what it does is it just spreads the bandwidth of this wavelength slightly more. That is needed so that I can amplify it further. If you do it this way, then of course this has become complicated because it is multiple stages now, but you get very low noise. So with that we did the Raman conversion and then try to see what has happened. So we did this experiment where we used a conventional laser and then we used the AAC source that Professor Anpeng suggested and then our own source that we have used. And then these are the results. You can see that if you use a conventional laser, you get 78% at this wavelength in band power, spectral purity. If you use a AAC source, as they suggested, we get 82 to 90%. And if you use our source, we are getting 99% power. So basically, it acts like a pure signal generator, but at optical wavelengths. And most interestingly, because we used a very low noise, low amplitude noise pump laser, these lasers, these wavelengths that you are getting, that are getting tuned, they are basically very low ring as well. So they are basically intercorrelated. Since I am not delving deeper into the physics, because I reduce the noise here, therefore the generated laser signals also, noise is reduced a lot. Okay, then let me talk about the second contribution. This is in the field of what is known as fiber supercontinuum sources. So to the people, everyone here, what supercontinuum generation is basically, you send in a narrow bandwidth optical signal called a laser into an optical fiber. For example, this could be, let's say, 20 gigahertz bandwidth. Then once it comes out of the fiber, it becomes a supercontinuum. Basically, it has hundreds of terahertz bandwidth. So since this entire broad bandwidth is coming from a single mode optical fiber, these are called as broad as lamp, bright as lasers, because the broadest and brightest source that we have in our universe is sunlight. Then after that, there is a facility called synchrotron radiation, which is like a very large area facility. But these lasers, they are basically tabletop. So it can be used for many interesting applications. And because of these unique properties, they are used for many applications, specifically in US, metrology, sensing, communications. Of course, they are used for biomedical imaging applications as well, which is optical coherence tomography. So our interest is in this. So that's just a brief introduction about supercontinuum. But however, because the way it is generated, it uses nonlinear effects inside the optical fiber. What you are doing basically is you are amplifying a lot of noise. So these sources are inherently noisy, and this has been a problem and people have been working on it. For example, how does that noise impact or affect biomedical application like OCT? This group, this professors at DTU has done this experiment where they have taken a cellotape, Scotch tape we call it in the lab, and then they use three different supercontinuum sources to image them. So basically they have layers. So this is the noisiest supercontinuum, this is somewhere in between, and this is the low noise supercontinuum. So if you see the image differences, for the noise one, the background is much brighter compared to the low noise one. So that's what is called signal to noise ratio. So what it means is that you can actually clearly distinguish different layers if you have a very low noise. So what it translates to biomedical imaging is, if you have some cancer that is developing, then you need to change that optical property. You need to detect that optical properties as early as possible. If your source is noisy, then you are not getting that information because that gets submerged in the noise. So it limits the early stage diagnostics. So of course, I am not the first one working on this problem. There are amazing professors, both in Europe and US, working on this, how to reduce the noise and all. Since I want to pitch my work, definitely, their solutions are definitely non-standard and non-complex. Currently, because of these solutions, these ultra-high resolution OCT systems are limited to very highly funded research labs in US. So my goal is to find a very simple solution. So, I'll just describe where is this noise coming from. So as I described, a supercontinuum source consists of a narrow bandwidth source at the input, and at the output of the fiber you get a very broadband source. Now, all these new wavelengths that are generated, or frequencies that are generated, are not present in the input signal. So basically they are coming from what is known as quantum noise or short noise we call it as. So what is happening is that in the process of superconducting generation, you are amplifying that noise basically. So how to reduce it is what the people have been investigation. So the other source of noise is if your input signal itself is noisy, because it's a the output wavelength is non-linearly coupled to the input wavelength, it gets amplified. So my solution is, why don't I reduce the noise here? Because this anyway you need a very complex solutions to reduce the noise. So again I use the same source that I have described for cascade Raman lasers. You start with a very low noise DFB laser, okay, which is like a semiconductor laser diode, which is of this much size. Then you do whatever I have done for the same source. You phase modulate it, line broaden it, and then you do amplification. Then you just connect a single mode telecom fiber. So this is the other important aspect of this work. Telecom fiber you already know. For example, you can buy a kilometer telecom fiber from Amazon for 3,000 rupees. On the other hand, a conventional superconducting source that you buy from a vendor like NKT Photonics uses few meters of what is known as photonic crystal fiber, which costs $600 per meter. Okay, so that's where this source becomes entirely very cheap now. So that's the experimental setup, and this is the superconductium generated in the lab. So you can see that this is the input signal, pump source we call it as. Then as I keep increasing the power, you get newer frequencies, and finally, let me fast forward it because of time constraints. So you are getting newer and newer frequencies, and then finally it starts forming the superconductium. So fiber is one mechanism to generate, but if you have sufficient power, you can generate superconductium even in a liquid droplet as well. Okay, but however, fiber is more useful form of superconductium because it can be used for many applications that I just mentioned. Okay, so what we did is we try to benchmark this source with the existing conventional superconductium. For that, we need to select the wavelength range that we want to operate. So we chose this long wavelength range where this superconductium is more flatter compared to the short wavelength range. There we observed that our power spectral density, that is power present per unit nanometer bandwidth, is almost 10 times higher than the commercial one that I am going to show. And the rin average over the entire spectrum is only 0.16%. So what it means is that if you have a power peak, your power fluctuates by 0.16% around that in any wavelength. So this is the comparison. So this is our work, and then if you see, many people have done very interesting solutions where some people observe more noise, and this is still the best work so far, where they reduce the noise to less than 0.05%. We are not the best, but second best. But however, this comes at a very low expense solution, where this can be further engineered, that we are currently exploring. But however, I want to mention that this comparison should be taken with a pinch of salt or a note of caution, because these works that are presented in this sorry, what happened? Yeah. Okay, so these works that are presented, these are called coherent superconductium. What do you mean by coherent superconductium is all the bandwidth that you have generated, they are all correlated to each other, their phases are correlated to each other. But the ones that I am generating, since I am amplifying the noise only, they are uncorrelated. So you don't have any correlation of each frequency, it doesn't have any correlation with respect to itself, its time, or it doesn't have any mutual correlation between two wavelengths, any other wavelengths. So it's incoherent. So it is only suited for low coherence interferometer applications like OCT. For example, this superconductium can be used for astronomical applications, pulse compression, where you can get a very short attosecond pulse, where you can study the molecular dynamics in real time. So my source is not competing with them in those applications, it is only competing for these type of applications. So at that I would like to conclude saying that we are doing these fiber lasers, especially low noise fiber lasers for quantum and biomedical applications. So in this tunable lasers called cascade round fiber lasers have interesting physics, where we observed that by using a properly designed pump laser, you can reduce the noise or increase the in-band power to the best possible. But at the same time, we are also working on this low-cost superconductium sources, still tabletop. We want to reduce the ring further, and since these are interesting for OCT applications, we are trying to see if this can be utilized for industrial applications here. However, industry is more interested in IV OCT, intravascular OCT, because that's where the demand is in the hospitals these days. So the good thing about this superconducting is you can convert that into IV OCT as application as well. So with that, I would like to thank everyone to present here. I'll be happy to answer questions. Thank you.